would like to share some of the like experience and the reason why that you make that move and how it like it happened.
Sure. So I worked for one of the grand old men in superconductivity for my thesis. It was at Harvard. And the guy's name was Mike Tinkham. He's one of the real founders of the field. And I worked for 5 years on something. And when I finished, I said, you know, I listened to him give a talk and it sounded wonderful, but I couldn't answer the question. I said, why did I do this? Who really cares? And I couldn't answer that question. I just couldn't. So I knew that I didn't want to do superconductivity. And I looked at all the people in my group, and there were these really smart people, these really great scientists. And I said, I don't want to compete with them. I could never do the sort of thing they're doing. They're just too good. So I wanted to find something that was new and different. And when I went to work at Exxon, and you know, it's an oil company. And the kind of science that was important for the oil company was basically soft matter science. So I started doing that.
Hey, Dave.
Although it didn't exist
Dave, about Exxon. So when was that? Why Exxon? Why didn't you go to university at that point?
Oh, I never wanted to go to university. I watched, again, somebody from our group, a fantastic scientist. He was a graduate student, then he became a junior professor at Harvard, which meant that he's not here anymore because he didn't get tenure, as all junior professors did in those days. But his name was Bill Scotchbowl. And I watched him as a colleague, as a graduate student, become a professor and never set a foot in the lab. So if you're a professor, you never go to the lab yourself. And I just like working in the lab. So I wanted to go somewhere I could just keep working in the lab. And so for 18 years, every single day, I went into the lab. And Joe, I bet you can't say that for yourself.
I cannot. Yeah, I cannot. Right now, I cannot even got the permission to come back to lab. Dedensify.
That's because you haven't figured out Harvard. You haven't figured out Harvard. Harvard, you never ask for permission. You only ask for forgiveness.
I see.
I go to the lab whenever I want. And I go regularly.
I see. Yeah, I went back for once and I got a warning.
Really?
Yeah, from Frank. Yeah.
Oh, geez.
Yeah.
You're lucky that you're not in Singapore.
If
you're in Singapore, you got to the lab without permission, you get fined. Actually, you get punished by not only the university, but also sometimes the government.
I see. That is more strict. Yeah.
Very serious. Very serious.
Yeah.
Yeah.
Okay, great. I think, yeah. So my second question is when I was a student, there's one thing from Dave that is really fascinating and attractive to me. That is one of his course at Harvard. That is that science and cooking lecture series. I think he bring those top chefs from the restaurants back to the Harvard and show the student how to make those dishes, how to those molecular level cooking. I think that is a very popular idea right nowadays in the Michelin restaurant. I was wondering how you have come up with those ideas and how you implement those scientific principles into those courses. And
well, the idea actually came about because we had a postdoc of Michael Brenner who came to me one day and said, let's invite Ferran Adrià to come to Harvard and give a talk. I said, who's he? He said, oh, he's the most famous chef in the world. I didn't even know that. I said, well, we can do that, but why would a guy ever come to Harvard, a chef come to Harvard to give a talk? He'd never come. He said, oh, come on, let's just try. So I wrote a letter and he translated it to Catalan, which is the language of Ferran. And we sent it by email. And 3 days later, he said he was coming. And so he came to Harvard. Of course, I'm always totally disorganized. I didn't do anything. And 2 days before he arrived, I said, what are we going to do? Well, let's have a talk. Let's have him give a public lecture but all the big rooms were booked. So the only room I could find was the physics colloquium room. And that year it had just been refurbished and had 215 beautiful new seats in it. It was a fabulous room. And then I walked by the room 3 hours before the talk, and there were people there waiting 3 hours before the talk. 2 hours before the talk, I walked by again. I had to call the campus police because there were so many people in the aisles, there was a fire hazard. And 1 hour before the talk, I had to go and find more breakout. We were going to webcast it. You didn't do that sort of thing those days. We were going to webcast it. I had to find more rooms to webcast it. The guy was like a rock star. Have you ever seen a rock star in a physics colloquium? I haven't. And then I realized, there's a real popularity there. And so we after his talk, we said, what can we do together? He has a lab, but I realized what I do in my lab is not going to be useful for what he does. So we said, well, let's teach a course together. So we taught this course, and he invited the chefs, and Michael and I did the science. And from that, it just became very popular. And so we just kept going.
Who were the audience? Who signed up for this, or who waited?
Okay, so the first time, again, you have to understand Harvard. People don't line up for physics courses. They just don't line up. We have this big building called a science center where they have these massive rooms, and they're empty and nobody watches, blah, blah. The first class, we had so many people trying to get in. The smart ones actually went to the class before, the physics class before, and got a seat and waited there. We had so many people waiting to get into a physics class that we had to have an auction. You had to have a lottery to join the class. And that doesn't happen at Harvard.
Yeah.
People don't sign up to take or line up to take physics classes. So
fascinating.
Kids like
I tried twice and never get into that class. So
Yeah,
that's the extreme of multidisciplinary collaboration, I think.
Yeah.
So is that the idea, the molecular, it's like a molecular cooking or like a molecular gastronomy? I forgot the exact words. Is that
what it is?
Is that being invented before your class or after your class?
Actually, molecular gastronomy was the words were coined by this crazy French sort of scientist. He's at the college. Oh God, I can't remember his name right now. I'll think of it. But they had a meeting. He and Dejean, Pierre-Gilles Dejean, ran this meeting at Erice where they invited chefs and scientists, and they coined the term. But the chefs hate it. They call it Modernist Cuisine because they say they've been using molecules all the time, and they don't cook with molecules. They cook with food. So we call it Modernist Cuisine.
Oh, fantastic. So I have another 2 questions, but I think maybe I can give opportunities to other like a panelist now if you have any questions to Dave before I maybe go too long.
So Dave, maybe I can jump in here. You have the season finale here. This is the last lecture of the year of 2020, of all years, 2020. Over the period of roughly about a year or so, you've asked so many challenging questions at the EML webinars. Are you ready for challenging questions today?
Oh, sure. I mean, unfortunately, I haven't attended during the fall because I taught at the same time as the lecture. I found I just couldn't skip my class. There was an error on the way we organized the timing of the class.
Yeah.
So I attended the first half, and they've been great. You guys should all be congratulated on doing this. It's fantastic. My only request is don't replace real lectures with this after the pandemic. As great as this is, it doesn't replace having real lectures. But I have to say the question and answer session afterwards, it's very different on Zoom. I don't know if you notice it. It's very different on Zoom. You have a much more intimate way of talking. Two people can talk to each other much more intimately than you can in an audience. I think that's one thing I was surprised about, and it's quite effective. And yes, I am all for asking probing questions.
Great.
That's the way
Thank you so much. Yeah.
Look forward.
Yeah.
Dave, you plan to talk about a fracture.
Yes.
You know how many experts in the audience about a fracture waiting for you to make mistake?
I know nothing about fracture, and I'll admit that right from the start. So that's the only extreme mechanics that we do, Shigang. So I'm going to learn. I'll say that right from the start, that this is more for me to learn.
Yeah.
You can tell me all the mistakes I'm making.
So just before Dave joined, actually, Sulin told me that there are like many people who are doing like a biomechanics coming from the like biology side, but very few of them are coming from the mechanics side. And I think Dave is very successful in this field, especially as a people coming from like more like a mechanics or physics side, especially like his recent like a work about those like a droplet sequencing is almost like bring this like enabled this wave of the single cell sequencing in the biology nowadays. So I also have the question to ask Dave, like is there any like a specific suggestions that from you, if you want to give the audience today who is in the mechanic engineering but want to do some like a biomechanics or biological work?
Before Dave answer this question, I think I want to say this. John asked a very good question, and that's an exact question that I'm going to ask for Dave. So how mechanics people should do biology, getting into the biology area? How would we use our mechanics background to push that field forward?
So I have two answers. The most important answers have really, really good students who are 10 times smarter than you, and then you can do anything you want. But the other thing is, what I learned long ago when I worked at Exxon was never ask what field you work in or what field somebody works in or what field you're thinking about. Just ask, is it good science? Is it interesting science? And if the answer is yes, just do it. Don't be afraid. So I never worry about what kind of science it is or what kind of who I'm interacting with. I only worry about, are they good people? Are they doing interesting things? And for me, anything I don't understand is often interesting. A postdoc I worked with early on in my career once told me that the good thing about doing something new is you never make a mistake. And you never make a mistake because you don't know anything. You're so stupid, you don't know that you're making a mistake. And there's a real joy in doing something new because you're never wrong. You're always right. So that's the way I look at things.
That's great.
Great.
Yeah.
So shall we keep going, or shall we maybe start to introduce them and start the?
So we start the formal introduction at the hour 9:30.
Okay.
So most people will just sign on at 9:30. Yeah, before 9:30, everything's informal.
Okay, great. Yeah. So my last question is, I think Dave is also a very successful entrepreneur, and like have so many companies that some of them are very successful. And so I want to ask this question on behalf of many of other attendees, like what's your experience to be successful in the startups, even you are in the academia?
Well, first of all, you know, I think I'm an experimentalist, and as an experimentalist, I'm never afraid to fail. And so there's a lot of companies that failed. So the success of the startups, for as many successful ones, there's many more unsuccessful ones. But that's okay, it doesn't bother me. And I mean, what I've learned is sometimes you do something and what's your goal? Your goal is to have as big an impact as you possibly can. And sometimes to do it right, you can't do it in an academic lab. You need a team of engineers to do something. And then it's better to do it as a startup. And then I don't run the startups. I'm not involved in that. But that's the best way to have, that's the way to have as big impact as you can. And sometimes the impact you want to have is not to write another paper, or not to publish, give another talk. And you want people to use what you're doing. And the best way of doing it is through a company. It's the only sustainable way of getting something out there, getting it used. And so just sometimes that just seems to be the only sensible way of doing it.
So as an experimentalist, it's like when we are running a lab, it's already like running a startup, not especially nowadays.
No, it's probably harder, right? It's harder to get money right now, especially in Boston.
So
in the Boston area, it's probably easier to get money for a startup than it is to get money to run your lab.
Yeah, Dave,
absolutely.
I want to ask you that follow up this. You were talking about this the entrepreneurship while doing research in university setup. I wonder, was there a moment in your professional career that you start to realize that, okay, to having this bigger or greater impact doing entrepreneurship is one way to achieve that? Or is that something deep in your mind that back in the early years you are passionate about this?
No, this year is the first year in 20 years since I came to Harvard. Every year I used to go for 2 weeks to Paris for a mini sabbatical in the summer to visit a former postdoc of mine, Jerome Bibet. And early on, he was much more entrepreneurial than me. But when I first told him about the work that we were doing in microfluidics, he told me about some work that one of his students was doing in the UK with a guy named Andrew Griffiths, who's since moved to the SPCI himself. And we looked it up and we realized that he was doing some very, very cool things that we didn't really understand. But it seemed like there was really some applications for that would be better done through a startup company than in our lab. So we started a small company, and it's a company that on the one hand was successful. It lasted for 10 years. It hired a lot of people. It raised a lot of money. On the other hand, was not successful because it never really brought a commercially successful, or it didn't last indefinitely. Eventually it failed, but it lasted 10 or 12 years. And we could only have done that through a company. And then I realized that, there are times where it just made more sense to do it that way.
That got started the Gates and then all other following up activities.
Yeah, also, I don't know, maybe it's just me, but I think my sense is that, again, in the Boston area, entrepreneurship and startup companies have become part of our culture here, our academic culture.
That's true.
And you look at you think that in the pandemic there should be problems finding jobs, but there are so many job openings for scientists around here because of the startup industry. There's far more jobs than there are people. It's just the job opportunities are just booming in the Boston area. I don't think that's true in general, but in the Boston area, it's really booming because of the startup industry. They're not being slowed down by the pandemic at all.
So do you encourage those like faculties, especially in the like tool builders, to like open their own company for like?
You know, everybody has to do what's right for them. And you have to do what's right for what you're trying to accomplish. And so sometimes yes, and sometimes no. And I don't think there's a hard and fast rule. And so some things we start companies, other things we don't.
John Hutchinson's here.
John, you're muted.
John, you're muted.
It's always going to be embarrassing to talk to your colleagues who know a million times more than you about something they do and I don't.
Right. All right. It's 9:30. So Dave, why don't you turn on your slides, and Jack can introduce you.
So I share my screen.
Yes, please do.
Yeah. Okay. I think Dave is definitely no need to be introduced, but for some of you who are new to this this topic, I want to introduce Professor David Weitz today to give the EML webinar. Dave received his PhD in physics from Harvard University, and then joined the Exxon Research and Engineering Company for 18 years. After that, he came back to academia. First became a professor of physics at the University of the UPenn, and then moved back to Harvard as a professor of physics and applied physics. He's now the Manning-Croft professor of physics and of applied physics at Harvard. So Dave pioneered in many fields, especially those like softer matter science. Established some of the most important principles in the soft matter. And his research interests are very broad, including material science, biophysics, microfluidics, and the flow in porous media. So in his recent work, Dave contributed significantly to the cellular mechanics and the droplet fluidics. He's a pioneer in applying droplet fluidics in high throughput biological assays, in particular in the single cell sequencing, which recently revolutionized the entire field of the biology. He is also a very famous entrepreneur. He founded many companies over the course of his career, such as the Capsule, One Cell Bio, those technology companies. And so I asked some of his students to help me look into those companies, and they believe that the valuation of those companies that Dave involved has been more than $3 billion nowadays. So next, let's welcome Dave to give us his lecture about the snap, speckle, and spot, the sight and the sound of hydraulic fracture. And Dave, the floor is yours.
All right, thank you, John. It's really an honor and a pleasure to be here. I listened to these seminar series at least when I wasn't teaching, and it's one of the real, if there is such a thing as a highlight in these tough times, this is one of them. I will say at the outset that Zhigang reminded me that I'm not going to talk about anything that Jia told you about, but rather I'm going to talk about something I know very little about. And a lot of my colleagues at Harvard and around the world know much, much more than me. So please bear with me when I tell you things that are wrong. All the mistakes are my own. None are those of the people who I work with. But we're having a lot of fun. We're learning a lot. And it's something that some fraction of our group does. It's the only extreme mechanics, I think, that we do. It's about fracture, and what's more extreme than fracture. So let me say at the outset that the work is done by Thomas Cochard, a postdoc in the group, Stefano Emi, who was a postdoc, he's now at ESPCI in Paris, and CJ Sun, a graduate student. We benefit enormously with our collaboration with Li Jizhao from China University of Petroleum in Beijing, with whom we share a sort of joint lab. So we really collaborate a lot with him and his group. And we also work with Martin de Hoop and his group at Rice University. So where does this title come from? I was trying to think of something, and I remembered something when I was a kid: snap, crackle, pop. I looked that up. For those of you who don't know, it's the jingo for Rice Krispies. It's a breakfast cereal from Kellogg's. I learned a lot from looking this up. This jingle was first recorded in 1932, a long time ago. It's one of the top 20 slogans of all of advertising. And if you look this website up at the bottom, let me see if I can get my pen to work here. Hang on, oops, sorry. Sorry about that. Yeah. Just let me get my pen working. Yeah, if you look at this slogan at the bottom, or this website at the bottom, you'll see that a science writer actually did an analogy with this jingle and with the glass transition. And what it really is that if you listen to Rice Krispies, they're a breakfast cereal, and you pour milk on them, you hear them crackle and snap and make sounds as the milk is imbibed into the cereal. And really that's what I want to talk about, is the imbibition or the entrance of a fluid of some sort into a solid and what happens to that. I want to point out also that the fluid doesn't have to be a liquid. Air also can play the same role. And so this is like another really fun pastime, and that's watching paint dry, but paint dry when there's cracks, and understanding something about the formation of the cracks, be it from a fluid going in or from drying, which is really like the fluid leaving, or air intruding, air invading into the system. And I'll show you an analogy that in some cases they really behave very much the same way. So the first system that I'm going to talk about is a fairly simple system. I want to talk about this system because we can do a lot of really interesting physics. It's something that's near and dear to my heart because I worked on it for years and years and years. And it also allows us not only, so this talk is not only going to be about studying the phenomenon of cracking, but also about developing new tools to visualize, to study, and to look at them. And hence the title, the speckle in the title, instead of the crackle. The speckle is using speckles from light, from a coherent laser light. And the spot, instead of the pop, is using a laser light to illuminate. I'm going to introduce some new light scattering and light imaging tools, or a combination of light scattering and imaging that allows us to study it. And this particular sample is a very convenient and informative sample, also something we know a lot about and that we can study quite easily. So it's just a colloidal gel. I'll describe it more in a minute. And we can either inject a fluid or inject air to create cracks. This is what it looks like. These are the cracks that we form. So I'll talk a lot about that. But of course, really, what this is motivated for in the bigger picture is actually fracking, hydraulic fracture that you do in now very commonly in resource recovery and oil recovery and gas recovery. And it's trying to understand something about the nature of the fracking that occurs, the water-based fracking. Now, I don't claim to actually study systems that are real like this. I will point out that fracking, particularly in this day and age, has a very bad connotation. It's not important right now during the pandemic. There's no shortage of oil whatsoever. But I will point out that, say, in the last 10 years, it's had a really big impact on the economy. You can argue it's good or bad. I don't want to do that. I just want to look at reality. It's qualitatively improved the way oil is recovered. For those of you who live in the United States, what you may or may not realize is that 10 years ago, we were completely beholden to very unstable regimes throughout the world that controlled the oil. We are no longer in that position. So that gives us enormous freedom, enormous advantages from a geopolitical effect. Fracking has a bad reputation, but it is a very effective way of recovery. And there may be problems such as seismicity-induced earthquakes. But if we understand more about it, we can understand how not to do it. It's currently very inefficient. But mainly the real reason, I don't do it for this reason at all. I do it because there's really cool and interesting physics, and we're really trying to understand that. And that's what I'm going to focus on. That's the only thing I'm going to focus on today. So let me go back to the experiments that I was showing you about, telling you about with these colloidal gels. So what they sample is, it's Ludox, that's colloidal silica. The size of the particles is a few nanometers in diameter. And with a variety of methods that are actually very well known from 30 or 40 years ago, we know how to induce a reaction that causes the otherwise stable particles that are moving around freely in the fluid to join together and form a gel. It's a colloidal gel. Its volume fraction can be between a few percent and 20%, 30% is very high. And it's relatively clear, so you can see through it, so we can do scattering experiments. And it has an elastic modulus that's of the order of kilopascals to maybe as high as a megapascal, very strongly dependent on the volume fraction that you begin with. And again, we understand a lot about these samples. I don't want to describe so much about the sample. I want to more describe how can we understand what's happening? How can we really understand the behavior? And so for most of the experiments I'm going to show you, we have a thin slab of a sample. It's like a Healy-Shaw cell, if you will. It's wide in this direction, and relatively thin in this direction. And we'll inject a fluid from one side. There'll be maybe an outlet here, and this fluid will hydrodynamically push the gel apart and cause a fracture. We can also just inject air or allow it to dry, and that's the same as injecting air, and I'll show you some examples of that. The advantage, the physics is essentially the same. It's just everything happens much more slowly because you're just dependent on the evaporation of the water, if you will, to cause it to dry. But the physics is more or less the same. So if we inject the fluid, this is what it looks like. If we increase the pressure as a function of time, we just use a syringe pump, and you see that we start injecting fluid, and we put a few kilopascals in. Roughly the yield modulus of the sample, and then a crack will nucleate and will flow, and we'll study the behavior and the propagation of the crack. Here's an example of that, just to show you all the cool things that happen. We're injecting fluid. This is the crack moving from left to right. There's another crack moving, and you see how the two cracks interact. You see that this crack, let me see if I can write on this movie, this crack has run into the other crack, it's run in here, but the other crack has moved in this direction, it's changed directions. That's not a random event, that's driven by the interaction between the crack. So how can we start to understand this? Here's some measurements. This is just looking at the image and measuring the speed and the acceleration of the two cracks. You see it speeds up, boom, and then the other one goes off in a different direction. So you get some kind of crack interaction, you get some recoil after merging. How can we really understand that? Well, Stefano is really a brilliant speckle scientist. He understands speckles like nobody else does. He was trained from a school originally from Italy, where they just knew everything about light scattering. His thesis advisor, in fact, was another former postdoc in the group, Luca Cipolletti, who came from that same school, and they just are whizzes about for understanding speckles. So let me show you what the sort of thing that Stefano did. He basically looked at imaging the sample, but he used a confocal microscope. So he just collects the scattered light. It's just the scattering from a confocal light microscope. He passes it through a confocal filter here, or a pinhole. And the point about the pinhole is that since this scattered light is from a laser, there are speckles, and by making the pinhole small, he can make the size of the speckles larger, but you still image. You're still observing the whole image. So each speckle actually corresponds to the scattered light from some region, and you get an image of speckles. And that's the important thing of the way you look at it. So here's an image, and you can see both the image and you can see the speckles in the image. And what he'll do is he'll average he'll image both the image itself and the speckles and learn something from that. Let me show you an example. Here's looking at the image, and you can see the crack propagating through the gel, but you can see there's speckles there. And so if you blow them up and look at the speckles themselves, you can see the deformation field, you can see the motion. And the thing is that what I'll show you is you can image the speckles themselves to understand something about the larger scale motion, and you can image the time dependence of the speckles to understand something about the shorter, smaller scale, faster motion. Let me show you what I mean. First of all, because it's a confocal image, you can actually see the three-dimensional image of the crack, and these are just showing the crack itself, and the arrows show the motion of the strain field around the sample. So let's go back and look at the behavior. Being able to do this, I showed you this ability to image the crack and measure the velocity, but now you can measure the whole strain field. You just look at the speckles over there, and you can measure the whole strain field. And these blue arrows show the strain field. The important thing is that the strain field around the crack is really all over. There's large strains far away from the crack, and that's what's driving this large interaction. That's what's driving the fact that this moves off in the direction it does. And then you can see just the divergence of the sample. It's plotted in red. You have the whole sample, the whole strain field of the sample while you're doing it. So let me just show you the steps that occur in these interacting cracks. First, you have the propagation. This is occurring because you're driving the fluid in, and you can see the strain field. It's falling off quite far away, but there's strain all the way around because it's a solid. It doesn't look like a solid because it's relatively clear, but you can see the fact that it's a solid because you can see the speckles and you can watch the way they move. As you come closer, again, the strain field now starts interacting. There's another strain field that's moving out in this direction from this crack and this direction from this crack, and you can see the way they interact. And that causes the fact that you have this long-range strain, that causes this crack to form, to change its direction and go in the path where you can get the most strain to pull it apart. And that becomes essentially normal to the first incoming crack. And you can see the large strains that are driving that. And here they come together, and look, you can see the whole strain field. You can see the interactions of the strain field like this, and then this is where they collide. And then because they're like this, because the strain is like this, the strain is driving quite far away. It's driving this crack to change its direction. Now you can see, because there's a combination of the strain fields, it causes this crack, the second crack, to recoil and to move off in a new direction. And you can see that, you can understand that, because you can measure the strain field quite far away. Okay, so let's see, what else did I want to show you? I wanted to show you the drying. Yeah, here's a case of the same thing. I just want to show you something that's very interesting. And it really, I think, is what allowed us to begin to really understand the physics of what's going on. We looked at this and we realized, actually, we were talking with Shmuel Rubinstein, and he was the one who really pointed it out so clearly to us. We looked just at a real space image of this. This was a case where we were looking at a drying crack. So the invading fluid, if you will, is air. We understand a lot about how that works. It's not so important for understanding the physics, whether it's air or fluid. I'll show you that later. But the beauty of air is that we're not driving it with a pressure, with an external pressure. So we can slow everything down and we can watch it more slowly. And when you do that, you see here's the crack. And notice here's the crack moving in this direction. Here's the air. And notice that there's a whole, let's see, yeah, there's a whole layer here of water. Here's the gel, here's the gel. There's a layer of water that's pulling apart. So you're cracking the gel. And this, in a sense, is what you have to do, because this sample probably has a few percent colloids, a few percent gel. It's mainly water. So in some sense, you're cracking the water. You're pulling it apart. Oh yeah, here. This is about 2% colloids. You're pulling it apart, but you always see this layer of water. And if you're used to working with these gels, you realize it's actually very difficult to separate the solid from the water, but that's exactly what you're doing. And so you have this layer of water that's always moving with the crack. And then if we looked at it more carefully, let's see, this, yeah, sorry, this, I have to play like this. The same thing, you look at, you see the water. And then when he started looking at it, we always saw this. We always see the water here. Another thing we can do is we can fit this to a sphere, and this tells us right here, that tells us that fits to a sphere. We know the radius curvature of a sphere. That tells us the difference in pressure. It's the Laplace pressure, the difference in pressure here and here. This is P1. This is P2. There has to be a pressure difference because of that radius of curvature. And you can calculate what it is, and it's of order, it's of the order of kilopascals, hundreds of pascals to a kilopascal, of that order, depending on the details, what the fluids are, what the surface tension are, what the radius is. And so it's almost like you have a stress that looks exactly the same thing. As a function of deformation, you have a stress that's causing this. And that gives you a clue as to what's going on. So CG made some beautiful experiments. Here's some drying experiments. He did it both with drying and with injection. And he just plotted these, took images. This is on the right is the real space, on the, fluorescence on the right, left is the real space. Again, the same sort of thing, but he plotted circles, and I put them before, but this is the radius of curvature is always the same. Now, let me see if I can play this again. And I'll put the circles there a little earlier. You'll see that whenever the these are just circles that I've just put there, or CG is drawn there, you see that if they fit the interface, it's always the same radius of curvature. Even when a crack changes directions, like this one is going to change directions and go in this direction, you see there's always water in front, and there's always the same radius of curvature. So that radius of curvature must be what's driving the crack. And so CG did some very simple calculations, and these are just order of magnitude calculations. He measured, he went to the rheometer, he made a sample, the same sample, he measured the yield stress, and for this sample, it's about 500 pascals, a half a kilopascal. And then he did the calculation. He measured the radius of curvature of these this front as it's moving forward. He did it with air and water, and he did it when he used a fluid. This is injecting a fluid, and they're about the same. They're all about the same value as this. So the values of the Laplace pressure and the values of the yield stress are more or less the same. So really what's happening, you can think of it this way, and I've just drawn this in a schematic way. This is the crack here. This is the tip of the crack. It's moving in this direction. This is either fluid being injected or air being injected. This is either at the injection pressure, so it'll be slightly higher than atmosphere, or if we're just injecting air, this is at atmosphere. And far away from the crack, it's also at atmosphere. So the pressure of the water, because of the Laplace pressure, the pressure of the water is lower. So this is a low pressure regime. And the unique thing about a colloidal gel is it's always under tension. You know that, for example, if you take a colloidal gel and you remove it from the walls, it pulls itself in. It undergoes what's called syneresis. It collapses in. And I can give you the mechanism. I can describe it if you ask me, but it's always essentially under tension. It's trying to pull itself apart. And so when you put a lower pressure here, it actually tears itself apart because it's being held to the walls and it's trying to pull itself apart. And that's exactly what you see. So you're seeing essentially a tearing mechanism of this particular sample because of that. And it's being driven by this low pressure that you're inducing because of the Laplace pressure. And that's why you always have this water layer here that's actually driving the crack, and you always see it. Okay, so Stefano also said, well, this is all very good, but as you make the sample more and more stiff, then the amount of motion you get becomes harder and harder to see. And he asked a question, could he figure out how to measure a very, very small motion with a very large field of view? Already you're doing pretty well, because what you do is you image the speckles and you can measure this the speckle, because before what you were seeing was just like a little point, a little speckle. You can measure the displacement of a speckle. So you can measure sort of micron type displacements. But he asked, can you do even better? And his analogy was, if you go for a walk and you're going to the big mountain, can you see a tiny bug far away and watch how it moves? And the way you typically do this is you literally watch the feature, you watch the bug move, you watch it move. This is exactly what we were doing. And so you're limited by being able to resolve something and watch it move. The problem is that as you make it farther and farther away, it gets harder and harder to resolve, and you can't really see it. So what else can you do? Can you somehow split the resolution, that is, you're trying to resolve something, with the sensitivity to motion? Can you somehow make far field measurements, try to understand the motion of something far away, looking at scales that are much smaller than the resolution you have? Remember, for an optical microscope, your resolution is set by the Rayleigh criterion. It's basically the wavelength of light. You want to know, can you do something even better than that? And so what Stefano did was he came up with something that it can measure very, very small displacements, really submicron, tens of nanometers of displacements over very, very large areas, centimeters, and relatively high rates, and in 3 dimensions, both in 3 dimensions in all directions and motion all directions. And he came up with the technique, and I'm going to describe that now, that he calls dynamic speckle holography, DSH, dynamic speckle holography. So how does this work? So basically you take advantage of interference. You go back to the light scattering of the sample, go back to the speckles. And so if you have 2 particles, you can image them, you can try and understand where they are, but a much more sensitive way that people have used for years and years is to take the scattered light and interfere it and look at the interference of the light. Then when one particle moves with respect to the other, the interference pattern changes. And so if you just measure the intensity here, you can see that it's changing, and it changes in time, it fluctuates in time. These are the fluctuations of the speckles themselves. And this is a very standard technique. It's very sensitive to the motion. And normally what it does is it measures the relative motion of just some collection of particles. But the way it does that is you look at the speckles and you just do a correlation function. You measure a single speckle. This is what it looks like as a function of time because it's correlating. You don't know whether the intensity is increasing or decreasing because you don't know exactly what the scattering is occurring, but you know that the intensity is changing, and it changes. You can see that it changes here when the particles move with respect to each other some fraction of a wavelength. A full wavelength is this much. Some fraction of a wavelength is how much you can detect it. And so the way you determine what's happening is you don't try and just measure exactly what's happening here, but instead you try and calculate a correlation function for something like that looks like this. You correlate the signal with itself. You can see I've written it down here. You would do a time correlation, and something like this will have an exponential decay of the correlation function. And that's just showing how the correlations of this, that shows the motion of one particle relative to another. But it's coming about because you're looking at the behavior of a single speckle. So just to show you that this works, this idea works, and you can do a full 3-dimensional image, Stefano did what I'm going to show in more detail. He just calculated the behavior where he imaged across something that's undergoing Poisson flow. So the particles are moving with that direction. And you collect the light, you collect you calculate the correlations, and you see the standard correlation function, exactly what you would expect to see for just flowing water. So we know this works. But now what we can do is go beyond that. Let's look at the behavior when you're doing something like one of these cracks. So here I'm going to show you what we're studying. This is the same thing. This is the colloidal gel. We're injecting, in this case, some dyed water. You see that a crack is forming. But now we're going to scatter from the samples over here. And so what we do is we set up the laser so that we image the sample and we collect the scattered light and image it through a diaphragm so you get this speckle pattern. Here I'm showing this is the speckle pattern. This is a blow up of the speckle pattern. And let me see, I think if I play this, yeah, you can see the fluctuations of the speckles. That means they're moving. This is looking over here, way far away. Here's the crack moving here, way far away. You can see that the speckles are still fluctuating. So you're still seeing motion because it's a solid. You're still seeing this motion, and you can see it just not from the changes of the speckles, not from the motion of the speckles, which is what we were seeing before, but rather from the fluctuations in the intensity. And so again, you can just look at the correlations, and now all you have to do is measure the average intensity in one speckle. You can average over some region to get better signal to noise, but you just measure the average decay. the initial decay of that speckle. And what that tells you is there's motion. It also tells you the direction of the motion, because the change is always proportional to the scattering vector, the vector that connects the incoming light and the scattered light. The difference is the scattering vector, and it's motion along that scattering vector, so you have a directionality of the scatter. So what you can do is you don't know exactly how much it scatters. You know how much it or how much it moves modulo 2 pi or modulo pi or modulo a wavelength. So if it doesn't move too much, you can see it decay, and you know in that time it's not moved more than a wavelength. So you can measure small motions. You can measure the speed of the motion. So here he's just coloring it by the speed. And you can see now it becomes very clear that the strain field extends far away from where the crack is. So you don't have to do it, because you have a vector, you can use a second laser, or you use a beam splitter to do that. You can bring a second laser in, and you can have two lasers that will get a Q vector in one direction and a Q vector in a second direction. So you can measure motion in both directions simultaneously. And here's the same thing now showing motion in both directions. I think some arrows some arrows begin to appear. This is the X and Y direction. And you can see now that you get a strain field far, far, far away from the crack. Again, it's a solid, it's being pulled away, but now the motion is tiny, but you can measure it because you're just doing this speckle holography. And it turns out that you can, with some very clever adjustment, it's more complicated. Now you have to use two scattering at the same time, two measurements at the same time. You can, by measuring the difference of two small wave vectors, you can actually measure something in the Z direction, the third direction. So now you actually have to make 4 measurements, but now you have a true three-dimensional motion. And this is just looking at the velocity field around the crack in 3 dimensions. And here it's shown here. So again, now you can see the wide range over which the strain is going, but these are minute strains that you can measure because you're doing this holographic method. You're doing this interference method, looking at the speckles and how they interfere. You can measure the motion of the cracks far, far away. And so again, here's some examples of watching this. This is a crack. And the important thing, and we saw why this is important when if we want to understand the interactions of the crack, we really do need to understand the motions, the strain fields of the solid far away. It's really a solid. We really want to understand the strains far, far away from where the tips of the cracks are moving. And that's what allows us to understand the interactions between the different types of cracks, the change in direction, really what's happening. And so here's just another example. Okay, so that's one thing that we've done. I want to just slightly change what I'm talking about. Still, we're going to use optical methods. We're going to add a different component to this, but we're going to look now not at something. Again, we'll continue to look at hydraulic fracture, but at a much stiffer material. This is a material, the materials that we were looking at were really relatively soft, so you could see the strain fields far away. The moduli were of order of kilopascals. Now I'm going to talk about moduli that are closer to hundreds of megapascals, something that's really very solid. And to image it, we'll again do our injection of fluid, but now we'll have to inject much higher pressures to cause the fracture. And in this case, we'll image it, but we'll use a very, very high-speed camera to image it. and just try to understand something about the nature of the behavior of hydraulic fracture. So this is what it looks like. We're going to use a high-speed camera. We need lots and lots of light to be able to do it. So we have some laser diodes that we can do it. The actual material that we use is something that's printed with a stereolithographic technique. Basically, you expose layers of the sample, and the exposure of the laser causes the resin to solidify, and you print layer by layer. It's made by the company that makes these printers is just a local startup company. Again, one of our former lab members is the person who designs the resins for it, so we know him well. And what's nice about that, because you're printing, because you're doing a 3D printing, you're sort of getting a layering effect to begin with. And this is not so different than the kind of layering effect that you might see in shale samples where fracture actually occurs. So you're getting something that's sort of similar to that, but it's not really meant to be the same. It's just the way we make the sample. And what's interesting is if you look, and I apologize for the size of this, but I'm going to tell you what these said. If you look at the modulus, this is the Young's modulus here for various kinds of samples that you actually do fracking with. You see that it's of the order here, gigapascals, it's of the order of 30 or 40 gigapascals. The sample that we're using, the modulus depends on how you cure it, how long you, after you print it, you have to cure it at a higher temperature, but it's of the order of a few gigapascals. Here's 1.5 and here's 3. We can change it a small amount, but you can see now it's not hundreds of pascals to kilopascals, but it's very close. It's of the same order of magnitude. It's gigapascals. It's of the same order of magnitude as what you might use in actual hydraulic fracture in the earth. So let me show you some images of what's happening. I'm going to show you now a series of images. I'm going to describe what's happening. I'm going to try and give you different ways. And again, as I told you, we're learning. We're trying to figure out what the best way to learn, to understand this, to really sort out what the physics is, to make the measurements, and to really adjust the sample so we can really see it and really understand what's going on. So here's a sample. This particular sample is a 5 by 5 square. These are each of these, actually, these are 5 samples. I'm going to draw here just so that it's more clear. It's something that looks like this. And so this is 5, this is 5. It's thinner this way. And in the middle, we've drilled a little hole and we inject fluid in the middle, and we're looking from the bottom. So you're looking up, and this is where the fluid is going to come. And I'm going to play these samples. They're recorded. You can see at 75 kilohertz, a very, very high speed image. And the time is about 1.3 milliseconds for the whole thing. And this is what it looks like. Let me just see if I can erase this. There we go. So you can see it. Now I'll play the images, and that's the fluid. The fluid is dyed. So you see what looks like splashing that comes in. But if you look more closely, what you see, these red or purple lines, or the red lines, are the fracture itself. The blue lines are where the fluid is. And I'll show you just the first few images. You see the whole sample basically is torn apart. The fracture spreads and tears the sample apart before any of the fluid comes. It's fascinating what happens. The fluid looks like it's undergoing some kind of turbulent motion. It's very difficult to watch. We haven't tried to focus on that, but notice how the whole sample is being completely torn apart. And the reason for that is that you've compressed the fluid. Let me see if I have a, yeah, here you've compressed the fluid. This is what it looks like. This is the pressure as a function of time. You've compressed the fluid. You have to put a pressure now, it's tens of 50 megapascals. This is, of course, what the yield stress of the sample is. The sample itself is of order gigapascal. Its yield stress is going to be something of a few percent. It's, in this case, 30, 40 megapascals. That's very consistent with it. So you compress it, and then you see the pressure fall off when it cracks. You basically are injecting it, and then you're just tearing the whole sample apart. When it cracks, it just completely cracks. It just pulls itself apart. At these pressures, you're actually compressing the water by a significant amount. So the first thing that's going to happen is you're not going to drive more water, but you're going to expand the water as the pressure drops. And it's going to take some time for that expansion to occur, and it's going to take some time for the fluid to follow the crack. It just can't follow the crack. The crack is just getting way ahead of the water. Okay, so what can we do to see something a little bit more indicative of this hydraulic fracking? Well, what's happening is that we're tearing the sample apart. It's the small sample. It's just being torn apart. So a simple thing is just to make the sample larger. Now, when you're 3D printing it, it's not so easy, but you can do that. And now what you see is you can get to the point where you get a fracture, but it doesn't tear the sample apart, and you have time to watch the fluid catch up to the fracture and understand something about the nature of the fracture. So let me just go to the next slide. Here are several samples where we've done that. And again, I'll show you all the samples. These are these larger samples. You can see they're 8 by 8 centimeters. The other are 5 by 5. We do the same thing. And now we see that I'm just playing this one. You see that happens. I'll play the next one. You see we can see the fracture, and we can watch the motion of the fracture and the motion of the crack in both cases. In all these cases, you can see that. And now let me show you here where I track. Again, I track the front and I track the fluid. And let's see what I'm playing. Okay, I'm playing just one. You see, and I'm going to go back and play this again. So now watch what happens. The first thing that happens is you see a fracture get way out in front of the fluid, and then the fluid is pushing it, but the front of the fracture is always out in front of the fluid. If you look carefully, you can see that. Same thing here. You have this large fracture, and then the fluid catches up. Same thing, large fracture, the fluid catches up. This one's a little bit different. The fluid is always just behind the fracture. So this one has a slightly different behavior. We tried to understand that, and what we realized is that in the first 3 cases, we had to nucleate a crack. So we had to put large pressure, and finally a crack would nucleate. In the other one, the crack seemed to nucleate right away. We didn't have to overcome this nucleation barrier, and it nucleated right away. When you have to have a nucleation, then the crack is way out in front of the fluid, and it takes some time for the fluid to catch up. In the other case, it happens much earlier. The fluid is always catching up. But in all cases, if you look carefully, it really looks like the crack is always moving faster and the fluid is trying to catch up. It's always pushing ahead. The crack front, the tip of the fracture is always ahead of the fluid. So now we can look at this in more detail, and we can watch this. This is the nucleation. So you can see at this point, the fluid is way behind the crack. It nucleates, and you see the crack is out, the fracture is way out in front. The next stage, the fluid catches up, but the crack is always, the crack is always in front of the fluid, and then finally you get a break, and the water, the cracking fluid, the hydraulic fluid, goes out of the sample. You get a fracture, the whole sample is torn apart. We can look at a lot of things. For example, if we go and we look at the behavior, you might ask, in fact, if I go back here, you might ask, when it's, I want to go one back. In this case, how fast is this crack propagating? What's the speed of the propagation of the crack? It looks like a sort of a stick-slip behavior. The crack moves and then stops, moves and then stops, moves and then stops. It moves ahead, then the water catches up, moves ahead, then the water catches up. So how can we understand what might be happening? Well, we can go and we can image the sample after it's torn apart. So here we can see that in this case, there is some real roughness. This is where the fluid is coming in. There's some real roughness, which is indicative of some nucleation process. You have to have somewhere where the crack begins to nucleate. Then if we look further out, so this is the sample here. This is the square sample. And this is this image, the blue image. And now I'm looking further out. I'm just taking images in this place. This yellow is here. It's coming from this direction. The water is coming from this direction. And notice you start seeing these rings. And if you look farther out, you see more rings. And these rings are called Walner lines. And they occur, you get this very characteristic periodic roughness that occurs when the fracture is moving at the speed of the Rayleigh wave. This is something Franz Papen pointed out to us, that this is real evidence here. The fact that we can see these Walner lines is real evidence that when the fracture is moving, it's moving in a stick-slip motion, but when it moves really at the speed of the Rayleigh wave. The Rayleigh wave is the speed of sound along an interface between a solid and a gas. So it's moving at the speed of a Rayleigh wave, which is what you might expect for this to happen. So now to try and understand something more than this, you can see that we can see some things, but we can't see everything. So we're trying to find new ways to analyze this. One way, of course, that I showed you is this imaging. We've gone to different samples. There are circular samples, so they're easier to work with. But now we also add 4 regions on each side where we have flat samples, and we put transducers so we can actually hear we can listen to the crack. We can try to identify the sound, the acoustic sound that the crack makes, with the hope that we can then correlate what we see with the visualization, with the optics, which we have good time resolution, but not perfect optical resolution yet. We can correlate that with what we can hear and try and understand something more about the nature of the fracture in the material itself. We also have modified the way we make the injector to try and avoid having this nucleation thing so we can better control it. We think we're beginning to learn how to do something like that. We can look for different propagation modes. This is all work in progress. But here I just want to show you what happens. These are some of the real early measurements where, again, we're back with our square sample, and I'll play this, and you'll see the crack propagating. This is one of the very early sounds that we record. But of course, if there's a sound, you should be able to hear it. So I hope this works. I won't promise it does, but I hope it works, that I'll be quiet for a minute and I'll try and listen to the crack. Of course, this is all down sample, but let me see if I hear it. So I could hear it on my speakers. I don't know. I hope you could hear it as well. But that's really the sound of the crack. And so now we can start to try and analyze things like this. And we're just trying to learn exactly how to do that. We're getting a lot of input from Martin de Hoop. We're trying to figure out the different ways. So for example, we could take that signal, and that was an early signal, but we could take it and look at the different places, the nucleation, the fracture, and the flow. And we can do a running FFT. So we take spectrograms, and instead of plotting it as a function of time, instead of plotting the amplitude, we plot the frequency spectrum. And you can see that there really does clearly look like there's some fractures that are occurring, some sounds that are occurring right where the crack is propagating. and we get a different signature as the whole as the fracture propagates beyond the nucleation, and a different signature still again when the fluid is flowing. So we're trying to understand this a little bit better. We try to calibrate the response that we get now. We're trying to be a little bit more serious. This is sort of a fun experiment. What happens? How can we get a response function for the system if you get a crack? And so what we do is we drop a steel ball on this and we listen to the signal. And I'll just play what happens. We take advantage of the camera, and we can actually watch the steel ball falling on the surface. Watch very carefully. This is very, very high speed, and it makes contact right there. And if you watch very closely, you can actually see a little bit of adhesion where it's pulling off. There's a little bit of sticking. And this is a chymogram. We can look at just one of the slices to the center and see how it measures where the impact is. And we can measure the response of the sensors. We see this ringing response, and we're pretty sure that the ringing response is just that we're exciting some vibration or some resonance of the whole sample itself. This is consistent with the speed of sound and the size of the sample. And this is what you would expect, that as you have some localized crack, some localized noise somewhere in the sample, you'll get a little ringing, you'll excite some response of the sample. We should be able to filter that out or filter the signal from that, and then watch what happens as we move as the crack propagates through the sample. And so let me show you some preliminary results along this line. What we did was we prepared two samples. Remember, I told you that if we cure the sample, we can change its modulus by roughly a factor of 2. So I can show you a softer and a harder, or stiffer sample. And we also used a more viscous fluid to slow the fluid down. And I'll show you the behavior of all three of them. And now to show you what we can do. This is also we measure the pressure where they break, and the color, they all break around the same level. If you did the same sample over and over again, you won't get exactly the same. There's some variation in where it breaks, but that's just the variation of the pressure that it breaks. So here's the first sample. So this is, let's go back and look. This sample one is the stiffer sample. So it's been cured. It's a little bit more rigid. And we inject water in this, and you see that the fracture is way out in front, and the water is following this, and it eventually breaks itself all the way across. If you go to the one that's cured and use water, in this case, you get something that's a little softer, and so now you get a fracture that doesn't break all the way across, and you can get this stick-slip motion. The water is catching up and pushing it in stick-slip. And you can slow it down even more by using a more viscous fluid. So now it fractures, but it doesn't go all the way out. It hasn't broken the sample apart, and the fluid is following it and slowly filling it. So now you have the opportunity to watch, to separate the fracture motion and the following of the fluid. And just by changing the viscosity, we should be able to study that. And again, we now can understand these things, and we can start to try and correlate both the frequency spectrum and the acoustics with the images and with the pressure that we measure. And we can do that by just doing a chymograph, measuring the intensity, for example, from the image. This is just a simple measurement. We can measure the intensity as a function of time along one of these lines as the crack propagates. That gives us an idea of what's happening. And so here's an example. This is where the fluid is moving. You can see the fluid moving. This is what the acoustics look like. This is what the pressure looks like. If we do now the chymograph, this is what the chymograph looks like here. And you can see that you get various structures here, the pressure, the fluid, and the fracture. And you can see these, if you look at this fracture line from the blue, and you can see there are steps, And that correlates to certain structure in the pressure, but clear structure where you can see little cracks appearing. You can see little rings appearing. You can hear the behavior, and that's right where something is happening. There's a little bit of motion. There's a little bit of pressure that's causing the fracture. So we're beginning to be able to separate out the occurrence of the fracture and the motion of the crack. We have several sensors, so we might be able to triangulate, find out where the position is. It's typically happening. It typically happens more towards one side than another, and probably by analyzing the frequency dependence, the frequency components of these sounds, there I think that the resonance should change because we're breaking the sample apart. These are all things that now are beginning to be feasible for us to make these measurements. And if we look later, once it's broken apart, again, you can see evidence. I don't think these are Walner lines, but you can see evidence of a stick slip motion of the crack moving, stopping, moving, stopping. You can see clear evidence in the roughness. This is just the outside edge of this one edge of the sample as it's fracturing. Okay, I think I've gone exactly for an hour. I think I better stop, and hopefully people will be asked questions. I've tried to show you, this is our foray into understanding cracking. I've tried to show you the things that we understand, many things we don't understand, lots of opportunities to learn. And somebody was asking me beforehand, they said, am I afraid of tough questions? No, I'm not, especially from people who know infinitely more than I do about fracture. Zhigang assured me that many people in the audience would know much more than me, and that's never hard. But please ask questions and tell us what we're missing. So with that, really, I thank you very much for your attention.
Great. Thank you very much for your very inspiring lecture, Dave. So I think there's are we gonna choose a question from the chat first, or panelist is going to ask a question first?
Yeah, Dave, can we ask you to unshare your screen so we can see people?
There you go.
Yeah. Right.
Okay, so maybe panelists can ask a question first, and then we can choose a question from the chat.
Right. So Dave, yeah, well, where's Dave now? Oh, Dave, you're here. No, I have a question. Now you have, I heard two materials. First of all, spectacular methods of doing measurements are just unbelievable. I didn't know you're doing this. So now I heard two materials. One is a colloidal gel. The other is a 3D printed plastic. Is that right?
Yeah.
Two very different materials.
Yeah.
Now, starting with a colloidal gel, I understand, I'm not quite sure how colloidal gel works. Are these particles, hard particles in water? Is that right?
Yes. Yes.
So,
exactly.
Yeah, and so this gel itself has some elasticity.
Yeah.
And then you showed a triangular zone with water. And how are you sure these are, this is a triangle of water?
I think that's a good question. The thing is, it can't be anything else, particularly if we do drying, because there's air,
yeah,
and there's water, and there's nothing else.
Okay.
And you can see a clear difference, and you know that you have to the solid. It's like you have something that's fluid. The solid is just this gel of the particles. So you have to, when you're splitting it, you have to first break the gel, but then you have to break the water.
Yeah.
It's like if you take any gel and you break it apart, you're really fracturing water as well as the gel.
Yeah.
The gel is what makes it solid, but the water is what gives it, for example, its bulk modulus. Its shear modulus is pretty low, but its bulk modulus is very large. It's just water.
Yeah.
And so you have to break the water. So all the energy is really coming from breaking the water.
So Now, let me try to understand further. So then you showed there is a circular in the wake of this triangle region. There's a circle. So the direction of curvature is such the pressure outside of this triangular water is actually higher than pressure
Exactly.
in the triangular region.
That's the cool thing.
Yeah,
That the water is at a lower pressure. It's a lower pressure than everywhere else. So that's why the gel is pulling itself apart, because there's a low pressure region in the side. Remember, the gel is under tension.
Yeah.
So it's a low pressure. It just pulls itself. It tears itself apart.
Yeah. I'm intrigued. The picture superficially looked like a, what we call ductile model, but the situation is different because the pressure inside actually is lower than pressure outside. Outside, the pressure is applied by it.
Yeah.
Right? Yeah.
Yeah. In this case, the thing is that if you increase the pressure and you drive water, you increase it, something, but not that much.
Yeah.
It's still going to be higher pressure.
Can I interject here?
Sure.
I also have this amazed by this phenomena. But Dave, I think that this is like in solid mechanics, we have wedging. We wedge a crack to propagate.
Mm-hmm.
I think the water, yes, the water at the tip of the crack undergoing lower pressure, but it's more like a water wedging. Pressure is there, so the pressure will apply pressure force at the bank of the crack and push the crack forward, right?
Mm-hmm.
Yes, except that the difference here is that the pressure is lower. It's not higher. So it's not like if I'm driving the water, if I put the water under pressure, I'm not. I'm putting it at a lower pressure because of the Laplace pressure.
Mm-hmm.
Lower, but it's still, that's the driving force. It doesn't matter, it's low.
Yeah. The driving force is that, but if the driving force in this case is not that you're driving the water, but you're allowing the gel to pull itself apart, because the gel really is under tension. If the gel weren't stuck to the walls, it wouldn't work, but it's stuck to the walls, it's pulling itself apart.
So yeah. The water, maybe let me interject. The water is playing the role of bridging the crack, whereas the pressure behind the water is playing the role of wedging or pushing the crack open. Or it's a cohesive zone type of model.
Well, no, I think that, say, the water at the crack tip is still undergoing pressure. So I consider this is like a water wedge. You see?
No, I don't, because I think that the water at the tip is actually a lower pressure.
Lower pressure than the ambient pressure. So it's
lower pressure than the ambient pressure and lower pressure than the gel, because far away, the gel is at ambient pressure.
But it's still under pressure, right? As long as it's under pressure, so it will push the crack back.
Well, I'd rather think of it pulling the crack, because it's under pressure is higher. The gel pressure is higher than the water.
Yeah, maybe, Dave, you need to educate a little bit about your colloidal gel. You keep saying colloidal gel is pooling itself. So let's forget about the crack for the time being. Yeah, let's say I have a piece of gel.
Yeah.
Lots of water, but then I have hard particles.
Yeah.
Hard particles in the gel, maybe particles interacting with each other so that the gel itself is an elastic solid.
Yep. So let's think, Zhigang, let's think how it's formed, okay? So you start getting these chains. I don't know if you can see my fingers. You get these chains and they're fluctuating, right? They're fluctuating. They're just undergoing thermal motion. And every once in a while they stick and they join and they form a bond. But if you think about they're fluctuating like this, the chances of forming a bond are most likely to occur at some place where they're not in their normal equilibrium. They're slightly out of equilibrium. So they form at something where they're just a little bit out of their equilibrium, out of their thermal equilibrium. And they're formed everywhere out of their thermal equilibrium. So it's like they want to pull themselves together. They'd like to reach a thermal equilibrium. So they're held in place by the walls, and they're always pulling on the walls. They're under tension. They're pulling from the wall. They're pulling on the walls. So if I cut it, it pulls itself apart. And I know that that's the case, because if I make the gel and I cut it from the walls, I just remove from the walls, it collapses.
Ah.
So that's the unique thing about this kind of sample. And this is actually the same for all gels. Any gel will be the same. It'll be under tension. It's got to be held in place by the walls. Otherwise, it pulls itself in.
Yeah, but
Even
our
your
hydrogel doesn't do that, right? Our hydrogel can be freestanding.
Your gel doesn't. Your gel doesn't.
So you're saying your gel cannot really be freestanding. If it's a freestanding, it becomes a sphere. Do you mean that?
If it's freestanding, then if it becomes a sphere, it's because the water becomes a sphere, right?
Yeah.
Gel itself won't become a sphere. So what do you mean by freestanding? When I say I pull it from the walls, I don't pull it out of the water. The water is still touching the walls.
Oh.
I disconnect it from the water. You don't do that. Your gel is always touching the edge of the water. It's stuck to the edge of the water. That's different, right? Here it can just pull itself in with respect to the water. If you did the same thing, if you could keep your gel in water and disconnect it from the walls, you'd undergo syneresis. All gels will do that. The solid part, not the water part, but the solid part is under tension. So you got to cut it just to cut the solid part, not the water. That's what I mean.
Okay.
So when you saw the gel pulling itself apart, it wasn't pulling the water. The breaking of the water was being followed by the pressure. You're breaking the surface of the water. That's what you're pushing. But you're breaking the solid part, which is the gel part. You're breaking that inside the water. And if you think about it, what you must be doing is you're pulling water out, right? Because you don't have new material, but you have the solid part spread apart. So you're breaking the solid part, but still staying in the water.
Okay, yeah, okay.
Next, maybe in the tethers safe. Can I ask a question? If not, maybe let's have the leaching gel ask a question.
Hello. Hi. Thank you. Yeah. Thank you, David, for giving us this very, very, very wonderful talk. Yeah, it's very nice, very great. So from your slides, from your talk, I have two questions. The first one, when you see at the beginning, you showed the string field of two crack propagation. You showed the crack, they have the velocity direction and the acceleration direction, they are different. So I just wondering, how can you test the different direction of crack propagation in this very small sample? Is the first question. The second question is about your the study of Speckle. So you put the speckle away from the crack, so the speckle can feel the crack motion, even though it is far away from the crack. So I just wondering, from the kind of the phenomena I observed is about the spacing cracking. So we can see the crack is not propagated always along one single crack. Actually, it's kind of nucleate from this crack, and get a spacing layers, get another crack and another crack. So if you think this kind of different spacking in the different along the different crack, which aligned in kind of with the fixed spacing layers, I don't think they put the artificially we put the speckle there to fill the crack away from the speckle. Do you think so? So I just
so let me try and answer both questions if I can remember them fast enough.
Thank you very much.
So the first question is, how do we know the motion of the solid and the motion of the crack? In that case, we were actually measuring not the interference effects, but actually looking at, we're using the speckles as just a way of putting structure on what we were seeing. So we put little pieces of structure, which are just the speckles, and we can see the tip. So we can measure the motion of the tip, and we can measure the velocity, we can measure its position, its velocity, and its acceleration. That's what we thought, just by imaging the tip. And by imaging the motion of the speckles, we could measure the strain field as it moved apart. So we could measure both of them at the same time. And in terms of the speckles occur naturally whenever you illuminate something with coherent light. So in fact, if you use a laser to illuminate things, you often try to get rid of them. In this case, we just take advantage of the speckles and just use them as little structural elements, like having that little bug, putting bugs everywhere. We're putting not structure, because it's very homogeneous, but we use the speckle as the structure, and we're just watching the motion of the speckles. So they occur everywhere, so we don't have to put them any place. We just have to illuminate it and collect the optics the way we do.
So may I understand that? So this speckle is different from the spacing cracking we observed, right? It's different. Just
the speckle is just something coming about from the illumination. Exactly. Mm-hmm. Sorry, I should have been clearer about that. It's just an illumination. You always see speckles when you illuminate with a laser. So,
yeah. Sorry. So may I go a little bit further? So if the speckle is different from the spacing cracking, so I just wondering, in your experiments, did you also observe the spacing cracking behavior in this small sample? Thank you.
So now I think what you're asking is, do we see multiple cracks and do we space them? And the answer is, we haven't tried to do that. Shmuel Rubinstein had a really great student who studied the interactions of cracks and gels doing fracturing. And he really looked for the spacing of cracks. That was Will Steinhardt. We haven't tried to control that yet. It's a really interesting question. We should do that. We just haven't done it yet. But to actually try and do what you're suggesting, to actually understand how the cracks space out, how the different cracks come about, we haven't done that yet. We were more interested in just looking for phenomena where we see two cracks interacting to understand the basic physics of the interaction of the cracks.
Thank you very much. May I know the reference that you just suggested? Thank you. This is last question, I'm sure. Thank you.
I don't think that they've published. I think they're still writing that paper up, as far as I know. If you email me, I'll put you in touch with the authors. It's beautiful work. It's fabulous work.
So Professor Rice has just asked a question in the Q&A section. Professor Rice has, if you want to ask a question here.
Okay, can you hear me, Dave?
I can, George.
It's actually two questions. The first one is there a D2O isotope effect, D2O versus H2O? And the second one is, if you put in a polymer that bridges surfaces like polyacrylamide or polyethylene glycol, does it make a difference?
So let me just think about that. First of all, I don't think there would be a D2O H2O effect, but I won't say there isn't. There may be some interesting, well, there must be some effect in terms of the formation of the gel.
There must also be an effect in terms of the strength of the HOH interactions.
Right, and so, but my view about that, George, is that it'll scale the interaction. So, it might change the modulus by a factor of 2 or 4, or whatever it is, but it won't change the underlying physics. It'll be the same. It'll just change the magnitude of things.
Interesting to see what the magnitude change is. Okay, what about polyethylene glycol or polyacrylamide?
So I think that that would give you some kind of adhesion, and I would expect there would be some kind of effect. I'd have to calculate the magnitude of that compared to the fracture energy of the water. surface energy of the water and compare that to that. So I don't know, George. It's a good question.
I mean, it does, these polymers do influence the nucleation of bubbles. And so, in fact, they'll stop them. This was a lot of what Abe Struck did with Missy Holbrook to demonstrate that this kind of effect was relevant, at least in part, to capillary attraction of water up trees. So it'd be interesting to know.
I know Abe's worked really well for where he used the gel. He measured the gel at the top of the leaf. I didn't realize he also put it in the middle. I'm going to look that up.
He looked at.
I know, I do. I remember exactly what you're talking about. Yeah, I remember exactly. It prevented cavitation, right? There were these
exactly.
That's a really good question, George. That's a really good question.
Okay,
so the answer is I don't know.
Yep, good.
It's a really good thing to try. We should try with those gels. Maybe Abe knows. I'll ask him.
Abe knows everything, so it would be good to ask.
No, that's a great question. And the answer is I don't know. But that's a really good question.
Another interesting knob for you to turn.
Yes, indeed. Thank you, George.
Next, Jimmy Shah.
Dave, very interesting talk. Thank you very much. This is about the second part of your talk, much stronger material with hydraulic fracking or fluid injected into the material. You showed that the crack front is way ahead of the fluid front. So when you have the crack front, obviously you have the material separating itself. What's in there? It's vacuum before the fluid gets into there?
Vapor, yeah. I would say it's vapor, but yeah.
It's so much ahead of the fluid itself.
Yeah, absolutely. It has to be. I would have thought it would be vapor, not vacuum, but essentially vacuum. It's not a fluid. It's a gas. But yes, it's basically yeah. In some sense, you're pulling it apart, so you're getting a cavitation of the fluid. But it's pushing the rock apart, and there's just vapor in there.
And it doesn't suck the fluid in there. Creating that vacuum.
Just a second. If it's vacuum, it's 100 kilopascals, and we're putting 50 megapascals. So it's a small difference. It's not a big effect on the scale of things. That's the way I look at it.
Okay. The second question is, what controls, why doesn't the crack branch or become multiple cracks? What makes it a single crack?
I showed you ones that are single cracks, that's what. So there are many times where it's too small to go up and down like a fracture in rock, and there's no heterogeneity to cause that. But what can happen when it nucleates is that, let's see, my hands. What can happen is you can get a crack running perpendicular that's breaking the sample apart. If you get a nucleation event, because you have to go to much higher pressures, you typically get that. So you get much more complex structures. And so actually, what I didn't say, Tomas worked very hard to make something where it would crack more uniformly. And then you don't see these extra perpendicular cracks that you will when you go to much higher pressures. And then exactly what happens, it's more random, it's heterogeneous. It happens somewhere, but you often see that. So you do see these perpendicular cracks if you go to slightly higher pressures, which you do if you have to nucleate a crack.
I see. Thank you.
Okay, so Robin, I think Thank you. Hi, Professor Whitz. First of all, this is Robin Bai from Northeastern, and I want to thank you for many years when I was at Harvard for shamelessly using your lab and pizzas at the Squishy Physics. Thank you very much. I have a comment. I know there's many polymer physicists in the audience, but following Jigan's question, I think the colloidal gel and the polymer gel are somewhat different in terms of the, so let's say for colloidal gel, you definitely have the short range correlations between the colored particles. But let's say for the polymer gel, especially let's say polyacrylamide, it's really very close to a zeta condition where all the correlations are screened. And therefore the polymer chain will just undergo a Gaussian distribution. Then of course I think that's why when Jigang was mentioning about our experience when we were doing polyacrylamide gels, you really can have some freestanding gel without the pooling stress internally. I think there's I'm happy to hear more comments from audience about these correlation point of views. So my question is about poroelastic fracture. So I think it's relevant. And especially when we were talking about, folks before were discussing this pressure down at the crack tip. I think we also had some suggestion and many modeling efforts on this, where the chemical potential at the crack tip because of the stress is reduced such that it drives water through, and it first embrittle the material because it has the gel has more water. Also, it can stretch the polymer chains locally, so it probably more it's easier to fracture. But it's on. I see it as an unresolved problem. But this is this is related to the earthquake, right? And also the fracking, because the increasing events of fracking is known to be positively correlated to earthquake events. So now the question is really, what's your what's your insights on solving or studying this problem of poroelastic fracture, especially from experimental point of view, quantitatively? How to quantify these?
Yeah, so I mean, I've always understood poroelasticity as basically just combining the fact that, or acknowledging the fact that liquid has to flow through the gel at the same time. And that must be happening because you're seeing the gel separate from the fluid inside. So the liquid has to flow. And I don't know, I think I can take a viscosity and a pore size, and I can get a length scale and a time scale. I can get a time scale for the flow, and I can look above and below that time scale, and that tells me something. And so I'm always just assuming that I'm looking at time scales slow enough that the fluid can flow. And if I have to look at higher time scales, then I should also include the viscous effects of that. And I haven't done that. I just, in my conceptual model, I just haven't done that. But obviously you have to do that. Is that important in fracking? I'm going to say it's not, because I'm going to say that the measurements that we show, to me, it shows that the crack propagates much faster than the fluid flows. So I think what happens is the crack propagates and then the fluid catches up. And I know there's models that people do for fracking that involve that, and I'm not familiar with them, or I haven't really tried to sort them out in my own mind. But I think that that's what's happening. In terms of seismicity, my understanding, and again, it's not perfect, people like Jim Rice know infinitely more, but my understanding of that, it's really occurs because of the fluid injection. So you'll get seismicity also if you're just injecting wastewater into the sample, and you're just basically changing the pressure distribution in the earth. And can you do better? Well, my belief is always you can do better if you understand more. And this is one small step to trying to understand more.
But I also want to add on to your points. I agree that the crack speed is usually much faster than the diffusion, but let's think about nucleation. So you inject water, let's do a desktop experiment, you inject water into a gel sample, but not close to the crack tip, maybe nearby. And then this changes the entire chemical potential map. And then this water may diffuse into the fault, what's that called? The slick plane or fault plane. And then the material will, the fracture can nucleate easier and maybe propagate. I haven't seen too much this experiment, but yeah, that's my interest.
No, I see what
point
you're
of
saying.
interest.
But my guess is that it happens too fast to allow much diffusion. But I don't know. I haven't done the calculation. It's a good point. And let me just go back to what you're saying about the gel. That I absolutely agree with you for polymer gels. That if there is no if you're really at some equilibrium, so there's no, if you're not pulling it out of equilibrium when you form the gel, so it's really, complete, as you say, completely screened. If it's really in its equilibrium position when it gels, then I agree there won't be much tension. And I'm less familiar with polymer gels, but I know that many polymer gels will cinerease. If you cut them from the side, they will collapse. And that's just, if they cinerease, they're under tension. If they don't, they're not.
Thank you.
So Jigang, maybe your gels are not under tension, but you should test.
You can actually, for polyacrylamide, correct me some folks, you can actually observe the opposite, the extrusion expansion effect. Slightly, very slight, for example, polyacrylamide, I think. But for some other gels, I know Xuanke had one paper about printing using this effect.
So let me see. What you're saying is that then in that case, the gel itself, there's a bit of an osmotic pressure that causes it to spread. I guess I can believe that.
It's like like you squeeze the noodle out of the spaghetti out of the.
If it's swelling, the only way it can swell is by sucking water in. So it must be an osmotic pressure difference that sucks the water in and causes the gel to spread.
Yep, I'm not sure about that. I'll dig into that further. But yeah, very interesting discussion. Thank you.
Great. So next is Teng Zhang.
Hi, Professor Weitz. Thanks a lot for a very nice talk. You do not only review fundamental physics, but also invent many new tools and methods to push the limits of the measurement. So this is Teng Zhang from Syracuse University, and I have two questions. One is for the technical question. The other, I want to ask some general advice for junior faculty. And my technical question actually is opposite to your study about the healing. So now you focus on the fracking by injecting liquid water. And I was wondering that after you have this crack pattern, is it possible you inject some other material, or even you change the surrounding stress to help the material heal? And even not fully heal, maybe you can help the material to regain some stiffness. I think that's related to your comments about the earthquake. The fracking that you change the pressure or stress state inside the fracture part. So I think if you can understand the healing, maybe you can guide people to do fracking, and then after fracking, you tell them how to do healing. So what's your insight on this?
Yeah, so I would say, let me say two things. I mean, first of all, if you have some kind of polymer or colloidal gel, there you might actually want it to heal. For example, if it's an elastomer that fractures, like a tire, you would like that to heal. And I think the only way of doing that is to somehow either have some resin in it or to have what George was talking about, having something that there's still some bonds that you haven't completely broken that can reform, or to have bonds that can slip and reform. And I know that Zhigong and Dave Mooney, with their alginate component in their interpenetrating gels, can make things like that. So you could get some healing. I'd say for solid material, it's more difficult for me to see how it heals. For an earthquake, my understanding there, the difference is that it's still under compression. It's always under compression. It's slipping, planes are slipping, but they're under compression. So if that's the case, they'll always be pushed together and they'll heal in that sense. I wish I could tell you how to make an earthquake heal, but I don't think I can. I don't expect to be able to ever do something like that, but it's an interesting thing to think about.
Okay, thank you. My second question is, I know you published many papers in different journals. I think one criteria we choose the journal now is the impact factor. And I think, so especially for junior faculty want to publish papers in the high impact journal, like high impact factor, but it's hard. And also I think some project maybe better suited for the high impact journal, or maybe better suited for the traditional journal. So for junior faculty, if we have several ideas, several directions, what's your suggestion or criteria for us to choose which research topic or which topics we should focus first, set the priority for different ideas? Thank you.
So I guess I'm old-fashioned. I don't believe in impact factors when I judge things. I believe in impact, not impact factors. And I believe that if you choose something that's super interesting that other people haven't thought about, and then you try and tell people, if you do something new, you try and tell people that it is, that's what's going to be important. And I think in most places in the US, I hope we don't evaluate things just by the impact factor. That's not the case in Asia, I recognize that. But in the US, I hope that we still ask what the impact of the work is. And for that, I always tell people in my group, let's worry about publishing the paper where it belongs, not about worrying about the impact factor. But students always want to struggle for the highest impact factor. We should really, all of us should agree as a community not to publish papers just because of the.
A second.
Okay, thank you.
I think Asia probably also should change, should change this attitude soon. Yeah. Especially nowadays, they're more like open source that you can, or like an archive, like bioarchive that you can put the papers there, even they haven't been really published.
Yeah, I think the bottom line is still do the best damn work you can. I think has the most impact, not that has the most impact factor, but has the most impact.
That's a great suggestion. So next is Manoko Akarin. Sorry, I don't know how to pronounce that.
Manu.
Don't worry, it's okay. Hi, Dave.
Good to see you. How are you?
Good to see you too. Very, very good. It makes me travel in time to hear you again and again. It's really great. Every time you know how to tell stories. Every time. I followed the work of Stefano because he was actually indeed working with Luca. And exactly. I asked him many times the question about he sees all this speckle variation and how he applied it beautifully in your work. And I was wondering if it was possible to see that in more solid materials like the one actually you showed us in the second part of your talk. Could it be possible to have speckle information there if the material was a little bit turbid? Or
you don't need turbid. I mean, the gel is not turbid. It's perfect. Yes, absolutely you can.
Indeed, the solid material will also show you some fluctuations?
Absolutely, absolutely.
So could you then predict where the crack should go if you could detect where the fluctuation happened before the crack opened?
Yeah, yeah, you could. I mean, you're not seeing fluctuations. You're seeing real strain fields, but you should be able to see the strain field in advance. Absolutely. I mean, you know, why I'm so excited by what Stefano did is that it should be applicable in all cases. The problem, of course, is that you would need very, very high speed imaging for which we have. You just have to image not the sample, not the front, but illuminate with a laser and image the speckles.
Yeah.
So absolutely.
And the second part also was very intriguing. The sounds that you showed us that goes with the crack, if I understood correctly. How can you be sure that these sounds are not the cavitation of the water that you're injecting due to the huge pressure drop that the water is submitted to when it's passing inside this very thin layer?
Manute, I can't be sure of anything. No, I don't know what it is. We're still trying to sort that out.
And did people put mics in earth when they do fracking to see if they hear something or signals that are not earthquakes? Huh? I'm speaking about the injection itself.
That's the only way they have of understanding it, is to listen.
They do that. Okay.
Yeah, and so this is the real motivation for this, is because ideally you'd like to triangulate the you'd like to have seismic detectors triangulate the sound and listen to where it comes from. And I don't think people do that yet, but I don't know enough about the way the fracking works. But yes, that's the only way you have a hope of being able to probe it. That's why we're doing it.
Thank you, Dave. I'll let the others ask questions then. Good to see you.
Good to see you too.
Okay, I will let the Professor Hai Chao Han ask the next question, since he's about to leave in 20 minutes.
Hi, Dave. Very inspiring talk. This is Hai Chao Han from UT San Antonio. I just have one question about the first part of the talk. You show a thin layer of gel that crack going through it. So the Speckle, you can see the big field. So my question is, let's say I have a bigger thickness, right? Either there is a crack underneath a layer of something. So I guess the Speckle would still detect the motion. So my question is there a way you can use the Speckle to detect the under surface crack, where it go, how big it is, that kind of information?
Yeah, so unfortunately, if it's a clear material, so you can get light through it, yes. So all the materials that we use are clear. We're using model materials, but if you're using rock, then no.
What I'm talking about, think about is like a soft, like a muscle or blood vessels.
The same thing. I mean, it's, well, let me be careful. You can image tissue fairly deeply with red light, but I think you still get quite a bit of scattering. So you typically have to use these optical coherence microscopy, things like that, to image deep. If you can collect scattered light, I mean, well, let me say the other possibility, of course, is that you can use Speckle from multiply scattered light. And I know that that will be sensitive to motion. We haven't actually tried to image that the way we do this. Here, we're really imaging the Speckle. With multiple scattering, I don't think you can image quite as well. Typically, you don't have that resolution when you do multiple scattering. You can do some. And so, let me not say that you can't do it, because I would have said you can't do this until Stefano did it. So somebody's really super clever like Stefano probably can do something good.
Thank you.
Thank you.
Great. So Brian Cox.
Good morning, David.
Okay.
What a lovely talk. Really, the images, of course, are very beautiful and very thought-provoking. So you showed images of one crack, and then a crack that ran into another crack. And when the two cracks joined, one of the things you pointed out was that a systematic change in direction of one of the cracks was always seen, which is intriguing. When you showed the images of strain fields around a single crack, they looked familiar from our traditional way of depicting cracks. You had some nonlinear zone which was more or less invariant, tagging along with the crack front. And when that's the case, we can say a couple of things. The plastic zone, generalized sense of the word plastic, is a material property essentially. And we can collapse that down onto, and the second statement is that we know that we can collapse that down into surface tractions acting just on the crack and treat the rest of the material as being linear elastic and do remarkably well. And then we have our traditional cohesive zone model. So here's the rub. Generally speaking, we want all of those modeling characteristics to be material properties, which is to say they're independent of the geometry of the specimen and the geometry of the cracks. But clearly when two cracks hit each other, that invariance is violated. But that still then leaves a question in my mind, and I'm sure many others' minds as well, and frankly, I'm not quite sure what people might already have done about this question. As one crack approaches another, especially since you see a very systematic change in the direction of one of those cracks, we might suspect that the modification of the, let's call it a cohesive zone, away from being a material constant is systematic, a systematic characteristic of the particular geometry of those two unifying cracks. And that raises the possibility that you might be able to model that systematic variation in the cohesive zones of those unifying cracks. And you've got a wealth of data in your imaging that would make that possible. And of course, the objective here is to keep everything in the cohesive zone regime of modeling, because we know how to handle cohesive zones in a very computationally efficient way. So can you please give some comment, Dave, on how much people have thought about this question of modeling the modifications that occur in the nonlinear zone as the two cracks join each other? Thank you.
The most honest answer is I have no idea. We don't do modeling whatsoever. I haven't seen anybody report this, but I'm not an expert in the literature. It's not something we've seen before. I may just have missed it. So I don't know anybody who's done the modeling. If I could just say one thing about that, especially if somebody would like to, I mean, it'd be fascinating to try and do this. It's just not something I know how to do, to be honest. But I'm not sure that it might be still all linear interactions that are driving this, because it's the strain field far away that's driving the direction. It's not the local crack. So you're right, you can do everything. The local cracks will be the same, but I think the direction is still the strain field from far away. And that, I bet you is still linear elasticity. It's just coupled to linear elasticity. So it's a little more complicated because the material is, there are two cracks that are happening. And if you just imagine that it's under tension, under linear tension, I bet you get pretty damn close to what you see. That'd be my guess. So it's under tension in all directions.
I think it's reasonable to ask our host, Zhigang, to make a remark at this point.
Well, I think some years ago, I saw people model interacting fracking cracks. either with cohesive zone model or just linear elastic. I think Dave, you probably have I think you have the right instinct. The crack probably is going seeking a mode 1 path tension. Yeah.
I don't think this is going to be the same as modeling hydrofracking in rocks, where I think they're probably going to be, the heterogeneities will play a big role. But again, I'm not certain.
Yeah.
Thank you.
The only reason I don't think it's been done is I've talked to Shmuel about it, and he knows much more about cracking than I'll ever know.
Yeah.
He didn't tell me it was done.
Yeah, Shmuel is more complicated. His situation is more detailed. It's not.
Yeah. The stuff they did with Will, it's more detailed. But still very beautiful.
Okay. Next is Victor Tai.
Hi, Dave. Thanks for the talk. I'm Victor Tsai. I'm a professor of geophysics at Brown University. The gel physics and imaging is really fascinating, but it seems to be in a very different regime than fracking in the earth. For example, like the fracture toughness regime and the far field compression and the surface tension effects. So I was wondering what your general thoughts are on about which of the knowledge gained in the experiments are transferable to actual hydraulic fracturing in the earth.
I think the point of doing the gel is that it's sort of cool physics, and it's a technique that should be transferable if we really want to the fracking of the tough plastics, but it's not going to be something that's relevant to the earth. But I think the fracking that we do with the hydraulic fracking of these tough materials, I think will have, well, I hope will have some relevance. I can't say it has enormous amount of relevance, but the goal is, the reason for doing it is to try and learn something about real hydrofracking.
Thanks.
Okay, next is Denise Kaya.
Hello, warm regards from Turkey. A very nice talk, very inspiring. So I would like to ask about the dimension of the cell, like the sample cell. How would that affect especially the crack tip, and whether when you're imaging, you want to see everything in focus, you just don't want to have it maybe like a thicker sample. But can you please comment on that? Thank you.
Yeah, I mean, ideally, you'd like to go, in fact, to a larger sample, because then, I mean, my view is that you essentially are pulling something apart, so you're getting a bending like this. That must be what's happening. And so if you can prevent that or put an overpressure on it to prevent that, then you could study more of what the real fracture is doing. But you're correct that you only have a few milliseconds to make your measurement, so you better be focused on the right thing. And we sort of carefully adjust where the geometry of the sample, and we scribe a line where we induce the fracture, just so we can do that, so we can have everything imaged correctly right from the start. But that's one of the challenges of the experiment.
I mean, if you were to make it thicker, would you have the same curvature of the tip that's propagating?
So the curvature, there are lots of curvatures, right? There's the global curvature this way, there's the curvature this way, and there's also whether the tip goes, it doesn't tend to go in a straight line, it tends to go in a curved line. So it's not a perfect penny-like fracture. And so all of those would be affected, I think. And again, it might be in the end something where we haven't tried this yet, but we could in principle try to have heterogeneities in the sample to drive the fracture along the heterogeneities. We've thought about it, we haven't done that. When you do 3D printing, you could in principle do that. That's good questions.
Great. Next from Ye Xu.
Hi, Dave. This is CA from Beihang in Beijing, China.
Hey, good to see you.
Hi. Yeah, good to see you too. Yeah, I'm really glad you choose to talk about fracture, especially in colloidal gels, because this is something we're also interested in working on that too. Yeah, I have one comment and maybe the two technical questions. One comment is since I've worked with Ludox, which I inherited from Eric Dufresne, I started doing that in your lab. So from my experience with colloidal gel, especially Ludox, I think one of the important fact that we consider the cracking, as we discussed before, I think one of the important factors is this is under drying conditions. So what we find out is that drying actually make all the particles pack closer, and then this shrinkage actually induce the internal tensile stress, which serves as the driving force for the colloidal gel cracking in drying colloidal gels, which might not be the same as the polymer gel that Zhigang worked to us. So that's my comment. So my two technical question is, one is, yeah, so related to that, the Ludox you're using, did you see like the packing fraction change under the drying, like before drying, after drying? Do you see a larger packing fraction change? And the second technical question is that because we have a lot of difficulty, like quantify the very accurate stream field using particle tracking, and your method with the laser speckle seems to be working beautifully. So my question is, like, what's the kind of requirement for doing this speckle imaging? Does it have to be like particulate material? If we choose to work on the fracture of the polymer gel like Zhigang does, would that still work? Thanks.
Yeah, okay, so let's see. I agree with you completely about the caution about just glibly telling Zhigang his gels must cinerise. They don't have to, you're right. And they may not, but in the end, the cracking of all of these things, the gel, the cracking, to actually induce a fracture, you have to break the water as well.
Mm-hmm. Yeah, that's true.
It's always the case. With the colloidal gels, of course, the volume fraction changes. If I see the water in the front of the crack, that's coming from the gel. So the volume fraction of the gel has to increase. And as you take water out, the volume fraction has to increase. So there's no question that it increases. The drying that we're doing, we're looking at the front, the drying crack. And so the volume fraction hasn't changed much there. It's changed a bit. It has to. That's what's pulling it apart. In terms of doing the speckle, I think there's nothing to prevent you from doing speckle in polymer gels. You might have to, you might want to put small number of a little tiny bit of Ludox, you know, 10th of a percent, 100th of a percent, just to get more scattering. But don't, in other words, if you're doing particle tracking, don't try and use particles that are too small. Don't track them, scatter from them.
Cool, that's great.
Yeah.
That's a good idea, thanks.
Okay, next is Professor Teng Li.
Thanks, Dave. I really enjoyed your talk. Very classic David Wise type of experiment. Simple, neat, thought-provoking, and fundamental science revealing. I really enjoyed, and it reminded me of the old days back in Pearsall or Maxwell Dworkin. Thank you. So my question is like this. So I think the observations of the cracking and the interactions between different cracks in your experiment, how dependent or sensitive that to the material property of the colloidal gel you are having? I think that's probably what make us think is that, for example, you have this capability to really see the displacement field and also then the strength field real time of the globally in the whole experiment, the sample. If you compare that strength field with the propagation, the strength field in the propagation of a solid, for example, a brittle material versus or a plastic material, how different is your material in comparison with a brittle solid or like a metal? So that probably will give us some insight that this crack interaction is different from those materials, or is that different from what's really in the earthquake? Because back in the 1980s, 1990s, I think Jigan and John knows much better than me on that. Then in the fracture mechanics, people studied this different cracks, how they interact with each other and in brittle materials. Like if you have large cracks, they probably shield the micro cracks. If you have similar cracks, they interact, they help each other in certain ways. So can you comment on that?
Yeah, so first of all, for the colloidal samples, and we actually understand a lot about them. We know how brittle they are. We know the yield stress and the yield strain. And the yield strain, the softer they get, the larger the yield strain before they become brittle. So that we can study and we can vary it. And I'm guessing for the colloids, it's not going to change things that much. However, for other samples where there's more plastic flow and things like that, again, I don't know the literature that well. I know just the stuff that Shmuel has done. And there he sees all kinds of strange effects, which I don't have them all in my head, but I think that you're correct that there's a lot of effects that you could try to sort out and understand. And there's a lot of opportunity to do that. So
yeah, I guess many things people did many years ago for fracture mechanics, probably you can try all these similar things in your material system. You probably see something really new. I mean,
yeah.
Because your experiment setup is simple. It's easy to really to design certain experiment to reveal different phenomena there. I really enjoy it. Thank you.
Yeah, as usual, it's our ignorance that prevents us from doing it. We should figure out more things that we can do. You're right. Those are good suggestions.
Professor Shuling Zhang can ask a question.
Hi, Dave. Shuling again. I want to say that, first of all, wonderful talk. I want to say that several years ago, I think 6-7 years ago, when I was in Boston area for my sabbatical leave, I sneaked into your group meeting all the time, and I enjoyed the pizza there. So thanks. I still stay very closely with your seminar. So I'm a registrar for your seminar. I enjoy the talks all the time. So I want to make a comment and then ask a question. I want to get back to the problem we asked. So you have a water linkage at the tail of the crack, and then you have higher pressure beyond water molecule or water regime. But my understanding, my comment, right? Maybe not right. My comment is that the surface tension actually attenuates the water pressure from the outer pressure. Okay, so I think the surface tension actually wants to do not want the crack to propagate. Okay, so but both the water molecules, the pressure in the water and outside will push the crack propagation. So I think really what constrains the crack propagation is the surface tension effect here. Okay, that's my comments.
Yeah, so I think you're right that the surface tension itself doesn't want the crack to propagate. It wants to pull it in.
Yes.
And so you need an extra pressure, and that the extra force is coming from either the pressure that you're putting with, if you're driving a fluid, or from the fact that there's flow along the sides as it's evaporating. That's what's causing the drive of the front.
Yeah. So because if I do a free body diagram analysis, this is usually what our mechanics people do. You take out the water, so you say that some pressure will apply on this bank of the crack, right? So that will that pressure will drive the crack propagation. And yes, surface tension will definitely do not want crack to propagate.
Yeah, but you're right. You're right, Julian. But I think that's driving the water cracking, because the water has to crack ultimately. The cracking of the gel is in front of that, and that's the tension in the gel that's driving that.
I see your point. I see your point. Yeah, very good. So I have a question. So since you apply this fantastic techniques on this colloidal system, are you thinking about using apply this technique to biological system? I know that you do a lot of biological studies and your students, your postdocs.
Yeah, we haven't thought about that. We should. We haven't thought about it. It's a good point. We normally don't want to crack and fracture biological systems, but that's not to say that doesn't happen.
Yeah, but for instance, our skin, right? Internal fracture of some organs.
Yeah.
Okay, thank you.
Thank you.
One is like the bullet penetrates through the body. It's very similar to this system. Yeah. So next is Rui Huang.
I'm going to have to just excuse myself and go to the toilet. I've been drinking too much coffee. I'll be right back. I apologize.
Sure.
I'll be right back.
Being a very long time, I think it's very hard for the speaker, I guess, for us too.
Yeah. Great. I think we have we reached a agreement on this problem.
Hey, George.
Yeah, Professor Whiteside.
George, it's so good to see you. George is muted.
He's putting it down.
George, you are muted. George, it's so good to see you.
I exist. More than that, I can't say.
George, we invited you first time, and many times both me and also John Rogers invite you to give a EML webinar. The invitation will always be open. Will you be willing to do it?
Yeah.
Oh, good. How about in the new year?
In the new year, we can talk about it. It's just a question of finding a time.
Finding a time.
Yep.
Yeah. Fantastic. It will be fantastic.
I exist to serve too. I exist and I exist to serve.
Thank you. It's so happy to see you.
Good to see you too, Zhigang.
I'll send you an email to arrange a time.
Okay.
Yeah.
Sorry. I'm back.
You look better.
I feel much better. You have no idea. Too much coffee.
Okay, I think it's my turn to ask questions. Sorry.
Zhigang, can I ask a brief question?
Yes, please.
Sure, go ahead.
The answer may be longer than that, but is this, I'm a second law of thermodynamics guy. And how do I think about this in thermodynamic terms? What is the driving force? And at the simplest level, is the crack propagation being dominated by enthalpy or by entropy?
Oh, that question is a long question. We have 100 years of answers in all directions. So it's literally 100 years.
Okay, well, Dave can convert it into 2 or 3 minutes. So it's going to be a great revelation.
Yeah, but actually, quickly, it's a very good question. So the first theory, a scientific theory about a fracture, is actually thermodynamic theory about Griffith. He was thinking about the fracture of a glass. In fracture of glass, it's mainly two kinds of energy. Energy stored, elastic energy in the body, and also energy stored on the surface as a surface energy.
Yep.
So he had a theory about minimizing the combined energy of elasticity and the surface energy. That theory works quite well. But after that, or when we apply his idea to something more realistic, something like steel, then thermodynamics it's not a thermodynamic balance anymore, because the steel has so much dissipation of a plasticity.
But it has to be thermodynamic.
Oh, yeah.
Because there isn't anything else.
Yeah. But it's not equilibrium. I guess this is the right word. It's no longer about equilibrium balance of, it's no longer about that. It's about dissipation.
Yeah, but if you define the starting state and the final state,
yeah,
then there has to be a thermodynamic connection between them.
Yeah, yeah. But you dissipate a lot of energy. It's not about minimizing energy anymore.
Well, but dissipation is another term that goes into the final state.
Yeah, yeah.
You've heated the environment or the water or whatever it is.
Yeah.
Do you have any opinions, Dave, on this subject? I mean,
Well,
is it entropy or enthalpy dominated?
I think it's mainly enthalpy, mainly, except in the case of the colloidal gels, where the fact that they're under tension is in some sense an entropic effect. And if you go to polymer gels, the elasticity of polymers is typically an entropic effect. And so entropy has to play a fairly important role, at least in determining the elasticity. But what's breaking is enthalpic. And if I could just say one thing, this is relevant, I think, to the thing that we do together with Sarah, and that is that, if you talk about minimizing energy, there has to be a way of comparing the different energies with whatever is allowing you to move from energy to energy state. And I think when Qigong talks about equilibrium, it's thermal energy that allows you to move and explore enough states that you can minimize it. But if it's a purely enthalpic effect, there'll still be energy that you still want to minimize it. But what takes you between state to state doesn't necessarily and may not be thermal effects, because the energy is just not enough.
But delta H over T is an entropic term.
Right. And if T is important, then it's got to be entropy. But I don't see that in many cases, if you're driving with these large forces, T is not important. If I change the temperature, it's not going to change anything.
Have you tried that?
No. But for example, if I change the temperature, say in a system where I can change it, say 10 degrees, the trouble is that's only a few percent, right? 10 out of 300 is not much. So it's a very subtle effect. And you'll never see something like that. But there's no obvious effect if it's an enthalpic behavior. And to change it more, there's all kinds of phase behaviors and other things that have much stronger effects. So
okay, you may be right, but it would be interesting to try a temperature dependence of the fracture energy.
Yeah. These systems, you'd be hard to do it with these systems. Maybe you'd have to maybe explore the phase diagram and do it under a higher pressure or something like that.
No, I would think it would actually be easy. You put your nice flat plate on top of a nice heated copper plate and let the two equilibrate.
The problem is, George, that in forming the gels, it's really a charge effect. And you change the screening length and the binding energy of the ions and the dielectric constants so much more than you change the mechanical properties. So there's just so many things that have a much larger temperature dependence that would obscure what you're really getting after.
Okay.
So I have a question here, following Professor Whiteside's question. So when Zhigang talked about this energy dissipation, so I consider we are moving from a equilibrium system or thermodynamic equilibrium system to a thermodynamically irreversible process. So since thermodynamically irreversible process usually tagged with entropy production, right? So that's the nature. If you have irreversible process, you have energy, you have entropy production.
Yes.
So entropic effect is there.
Yeah, sure.
Is that my understanding is correct? Sure. So as long as we have plasticity, we have the entropic effect is there, right? And because for plasticity, you generate a lot of heat.
Yeah.
Right?
Yeah. Sure. Now, actually, yeah, I agree. Now, since Dave and George, two of my heroes are on the same screen, I actually want to ask a more elementary question. Cannot waste this opportunity. You guys often choose weird problems and turns out to be spectacular. Can you say a little bit about this? Maybe George first. You're the weirdest problem chooser often, and then turns out to be spectacular. I have so many examples. For example, soft robots, all these things. Can you relate some of your experience?
Well, my summary would be if somebody else is working on it, we don't. That's it.
Say it again.
If someone else is working on the subject, we don't work on the subject.
You want to do something different.
Yeah. I mean, why do what other people are doing?
Yep.
Why should we work on Speckle when Dave has already thought about it a lot and worked hard on Speckle and done spectacular things with Speckle?
Yeah. So let's be specific. I have a few examples. For example, you started to seriously look at these soft robots driven by air.
Yeah.
What were you thinking about?
Soft robots and organisms. I mean, organisms basically work by mechanisms and architectures that are different than you see when you are, trying to make hard robots. One is not necessarily better than the other; they're just different. And so there's a particular need there, which is, in the long run, I think, contribution to public health and to what is it that you can do to replace nurses' hands for giving care in hospitals and things of this sort. And we haven't, for a variety of reasons, gotten to working on the biomedical applications. Well, we have begun to work, but we haven't made a major effort that way. But that underlying notion of what does a structure look like of an organism that you can replicate. An organism is soft generally. How can you replicate that in polymer? And the easiest way of achieving actuation is pneumatically. So, I mean, one key element is making things as simple as you possibly can, something which Dave has done spectacularly well. And then if you're going to make it simple, other people can reproduce it and make it better.
Yeah, Dave, I guess the same question. What made you choose this problem to work on? This problem, hydraulic.
So let me say that, George is also one of my heroes because the way he does it. I always want to be like George. I want to be able to think as many projects as George. But it's interesting. I've never heard him ask the question, but I do exactly the same thing. I'd rather be first instead of being best. I always tell my students, it's better to be first than being best. Ideally, you'd like to be first and best, but really you want to be first. And if too many people jump in, then you want to just move on to something else.
Yeah. So for the particular hydraulic fracture you're talking about,
thank you very much for calling.
What made you get into this problem?
Just I looked at all I asked my friends from Exxon days, what are the biggest developments in the petroleum industry? This was back in 2008 or so, where the price of oil was really high. And they told me there are three things. One is horizontal drilling. Second is multiple scattering of acoustics to do imaging. And third is fracking. And so I've done multiple scattering before. I don't want to do horizontal drilling, but fracking seems like a really cool project. That just seemed to be a really cool thing that I wanted to get people at Harvard working on. I think we did. Because I think it's just the kind of thing that we as a community know how to address.
Jigang, can I follow up your question to George? Yeah, George. So when John Rogers was presenting his EML webinar, he told us this two famous questions he learned from you. What's new and who cares? Right. Your answer to Jigang's question that we don't do if other people do, we don't do it. Then that addresses the what's new. Can you comment on who cares?
Well, who cares is it always takes us longer to do a research project than I imagine it to even be possible at the beginning. And so one way of classifying research projects is to ask who cares about the research in the long term, not in the short term. So Dave's work, the stuff that he's talked about today, deals with energy. Now, I don't know exactly how it fits into the grander scheme of CO2 reduction and things of this sort. That's a different question. But people care about energy, hence they care about fracking. People care about replacing people by machines, and hence soft robotics. And people often have an odd view of robotics, which is that it takes good people and puts them out of work. But in fact, the initial, good example of initial introduction of robotics were washing machines and dishwashers, which took half of the US population, which otherwise known as women, and replaced them from really boring jobs and let them be bankers and work for Goldman Sachs and work for Dave and do whatever, sort of behavior they wanted to do. So robotics enable people to take jobs that human beings don't want to do and let machines do them. And then the people can go off and do other things that are more interesting and more challenging and require people more. So if you look carefully at these kinds of inevitabilities, things that are going to happen, we are going to have more work that needs to be done than we have people who are going to do the work. You'll find it's not so difficult to distinguish one kind of job from another kind of job, one kind of research project from another kind of research project, in my view. Dave may want to comment on this too.
George, I agree completely. I even ask my students, I say, the question you have to ask is if you're really successful 5 years from now, what will you have done and why will that be important?
Exactly.
If you can answer that, then you should do it. If you can't answer it, you have to ask yourself, why are you doing it? Why are you spending your time doing that and not something that you can answer that question?
Right. And, this whole question also applies to the issue of technology translation, because the issue that comes into, making a small company of a new technology is often phrased in terms of, well, you think you're going to make a lot of money. I don't think anybody who does technology translation does it for the money. It's just too hard and too improbable and too this and that. But the thing is that in order to arrive at a new, real successful technology, the rule of thumb is my rule of thumb anyway, is it takes about 20 years and about $100 million, no matter how you do it. And people are only going to do that if they care about the result. And that means they care about it. They're going to do it at scale. They're going to continue it because they think it's important or interesting or exciting. So the idea that the university is a closed box and we do whatever we do just based on what goes on inside can't possibly be right. My research grants are funded by my neighbors who do so because they think it's going to make a better world. Somehow, they don't know exactly how, nor do I. And so that underlying issue of how you manage to distinguish between projects that are worthwhile doing and projects that are not, at least in part, depends upon the answer to the question, does somebody care whether I succeed in this and its derivatives or not? And the answer to me has to be yes. It's not a question of doing startups or any of that. It's a question of deciding what's worthwhile doing and what's not worthwhile doing. Dave, you want to comment? You've been very good.
I agree with you completely. I also agree that I am eternally grateful to, as you put it, your neighbors or to everybody else, including me. We pay our taxes, and that's where we get a lot of our support.
Yep.
And I feel obligated to try and give back to society since they're supporting our research. And society, you know, they're not interested in my little things that I learn. They're interested in something else, and they're interested in things that have impact on society. And you know, will they create jobs? Will they improve our economy? And I think you can't dissociate that from what you do. Not everything we do will do that, but if there's some opportunity that will, you have to do it.
Yep.
So I feel obligated to do it because you know I'm being supported by the public. So
does that answer your question? Okay.
Thank you very much, both of you. It's really inspiring. Really appreciate it.
Yeah, and George, over the years, when I interact with you, the other aspect I was just deeply touched. You care about people, especially people that are working under you. You want to find them great job and good direction in research. And you do it over and over again with many people. How do you do that?
Well, you know, the thing about the students that we get is they're all, not all, but most of them are bright enough and creative enough to do really interesting stuff. But people work best for themselves. Mm-hmm. So if they want a good job, then they will work best if the prospect of a good job is in front of them. Mm-hmm. And what we need to do as teachers is to help them to become productive citizens. And that's quite different from we as teachers have the job of getting them to produce papers that make us more famous. Mm-hmm. So, you know, one of the wonderful things that happened to me when I came to Harvard was that I had a series of instructors, one of whom was my secretary. And one of the things she pointed out fairly early was that the major skill of running a research group was to realize it was a social organization rather than a scientific organization. And that what you do is listen carefully what people tell you they're interested in and they want to do and try to help them to do that. So the answer isn't very complicated. It's just a question of do you make the focus the people in the group or the scientific product of the group.
Yeah, Dave, in your case, you also turn out many successful researcher. And also your research group was just enormous, always 100 people or something. How do you do that? You clearly cannot interact with everybody with the same amount of time. It's just not possible, not enough hours. How do you do that?
Yeah, well, let's see. So you're asking two things. I mean, I guess I'm probably not as good as George at letting people run, but I add one little fact, and that is that I think that if we all do good research, it benefits everybody. So what I try to do with the people in my group is make sure they don't do bad research. Mm-hmm. And if they're capable of steering their research themselves, I let them. And I always believe that I'm not the smartest person around. And my group is going to be successful if everybody contributes. And so I want to see us as a group do the best research we can, not do the research that I want to do. Hmm. So I want the definition of the best research to come from wherever it is. Whoever has the idea, whether we read something, if somebody brings it up, that's what we do. And it's often not me who thinks of the ideas, it's people in the group. And that's what I like. I think that enriches the whole group. And you're right, I don't spend time with everybody. I think there's a law of nature. It's what I call the 20-20-60 law. So in any group of any size, 20% of the group, and it could be 10%, it could be 25%, they're the ones who do 90% of the really cool stuff. And there's 20% of the group that you just don't know what they're there for. And there's 60% of the group who are good, but they're not great. And I learned this law when I worked at Exxon, because at Exxon, when I worked there, they had the Jack Welch Management School. So every year they evaluated, they rank ordered everybody in the organization, and they fired the bottom 10% every year. I was there for 18 years. That's 180%. That's, you know, a factor of 2 or 3 turnover. So you'd think the organization would get better, right? Never did. Never. Because that doesn't work. It just doesn't work. You got to accept the fact that there's always going to be that law. No matter what organization you have, no matter where, it's always the same. So you can get rid of people, you're always going to end up being the same. And so once you accept that, then you, at least my view is, you know, for the bottom 20%, I try and make sure they find something. For the middle 60%, I encourage them, I work with them, but, you know, I wait till they bring me something. And for the top 20%, I just enjoy. I just work with them and enjoy them. They're the ones who I put most of my attention to because I have the most fun. But I care and I want to make sure the others do well. But I always accept the fact that there'll be a gradation of contributions and capabilities. And that's just natural to any human organization.
Yeah, Ray has some question. Ray.
Yes, thank you. I think this is a very wonderful discussion. Thanks to David and George to share with us this. And also, I have a couple of comments, maybe also a question for David. So great talk. I enjoyed very much. Actually, I'm giving final exam right now, so I have to pop in and out a little bit. Some students keep popping in, ask questions. But anyway, so I stayed as far as I can. So this experiment is beautiful experiment. I think I think it reminded me something I've seen some years ago from my colleague, Ravi Chander. He actually also tried to do something similar, pumping water into a transparent gel and driving cracks, horizontal cracks, sometimes multiple cracks propagating. So simulating the actual fracturing process. So I remember he showed me some videos how the crack is growing, sometimes even branching. Of course, it's different kind of gel. I think he used the polymer gels. He didn't use any of these beautiful measurement tools. It's just basically viewing it, seeing it, transparent the paths. I'm not sure if they have published anything yet, but I will talk to him, see if there is anything to learn from what you have been doing. The other comments about modeling, I think also, as far as I know, there are quite a lot of modeling work in the fracking area. I know there is a group in Minnesota who does a lot of theoretical works. I'm not really following that as much, but I think there are some interesting ideas about at the crack tip, there is a water, or sometimes they say that in front of the water, there is actually an air gap, right? Because the water cannot go all the way to the tip. So that is one of the models I've seen. Now, on polymer gels, I know, for example, Bob McMeekin have done modeling using a cohesive zone, assuming there is a bridging zone with liquid and the polymer chains. So they can actually see how this bridging zone works. I think that is a kind of similar picture to what you have shown with that water bridge, but of course you don't seem to have any solid in there, right? So you believe it's just pure water. Of course, the loading is also different because I think what he did also, sometimes we also followed that as well, is about the remote tension. So in this case, your loading is actually from internal pressure. So that kind of changes maybe the stress state near the crack tip. But if I think about back to old days when we do linear elastic fracture mechanics, the remote tension and internal pressure, they are almost equivalent in the linear elastic fracture mechanics, right? Basically, the superposition of hydrostatic pressure everywhere. And then the solution for Griffith's crack is the same as the internal fracture. So I guess my question, I'm still trying to think, I need to think more about this, is what would be the stress state along that crack plane? You have a high pressure in the back, and you have a water zone, maybe a constant lower pressure, and then you got a crack tip, the intact part, they're still connected. Are they still under tension? Or basically the stress doesn't seem to be continuous along that plane anymore, right?
Yeah, it's a good point, a good question. I think that they are still under tension. So I don't know the work that you're referring to, but I would have said that this is exactly the same, that there is a tension in the gel that's pulling it apart right at the tip.
Right.
And the water pressure is driving that tension. The fact, but what's interesting is that the water pressure is lower because of the Laplace pressure. I think that's the way I look at
right.
it. To me, it was a surprise when we saw that water. It's not what I thought was happening until we saw that. The person who really clearly thought it through, by the way, is CG, my graduate student. He's the one who taught me exactly how to think about it. He convinced me.
So I
think it sounds like it's the same as what you're talking about. I apologize, I don't know the work.
Yeah, that's okay. I think it's personally, I feel just like what Zhigang said very early on, superficially or intuitively, it looks like a ductile model, but there was the internal pressure driving. And my feeling is that you can probably model this just like a ductile model. Instead of a constant tension in that bridging zone, you have constant pressure, but it's lower pressure than the outside pressure. As a result of this outer pressure pushing this thing through. So you have a sort of between the outer pressure and the front, not cracked part, there is a sort of a zone connecting those two parts that just develop as a result of this pressurized fracture.
No, I mean, I think it's very interesting. And look, I was being a bit glib because, there has to be, there's probably not a full pressure gradient at the interface in the water, between the gel surface and the water. I don't know if there's a surface tension of the gel. I'm not sure. I'm not sure about that. In the water, there might be. It'd be a different kind of energy. There's probably, somebody mentioned poroelasticity. There's probably some frequency dependence of the flow of the water that I've just glibly ignored that you have to bring in. But what's interesting, I think, is that it would be, I think, quite interesting to ask whether you took the same model and just put a negative pressure, but
right,
still one that drove forward, whether you get the same behavior.
Yeah, I think
that would be cool. That would be very cool.
To think about. Thank you. Great.
Thank you.
Dave,
you should do that. I should come and talk to you.
Me? Sure. I'll be great. I'll be happy to.
Okay. Talk about your colloidal gel again. Maybe just asking more elementary question. So, for example, many years ago, not many years ago, some years ago, you worked with Franz Papen with a crystalline colloidal gel, right? So to talk about a fracture, first we need to understand something about cohesion to begin with, or what gets things together. So for crystalline colloidal gel, that's very clear. You can actually colloids, particles, form a crystal. Then you can say, I fracture this crystal, right? And perhaps, have you done experiment like that? I'm
just trying to think if we've done that. The answer is no. What Jolt is doing, Jolt Turdic is doing is looking at plastic flow of crystals because of the defect motion. So we haven't actually fractured it.
Yeah.
It's harder to fracture a colloidal gel because the ones that we're doing are truly entropic only.
Right.
So they exist because you fix the volume fraction. So you have to maintain an osmotic pressure to hold them in place. And so it's hard to get to fracture it.
So let me understand that this is probably crucial. You just mentioned something. So in the gel you're using today, demonstrate today, so that these are the particles don't have enough adhesion. So it's almost like a gas. So if you have more water, these particles will be separate far away. Is that?
No, it's quite the opposite. It's quite the opposite. We start like that, but what we do is we start with particles that have locally a fairly strong repulsion. So if they diffuse, they come close, and then they can't come closer than some distance, and so they never touch one another.
Yeah.
And we use a sort of a delicate way of doing it, but it's not that important how we do it. We turn that repulsion off.
Yeah.
So that when they diffuse and move, if they come close to one another, they stick, and they stick irreversibly. And that causes them to form this gel structure because they're stuck irreversibly. And so at that point, they no longer diffuse.
Oh, so they almost like it's almost like a glass. They form not crystal, but they have enough adhesion. They actually form a solid structure.
Yeah, yeah.
Okay.
Yeah.
So then, if you have
the reason you can call it a glass, if you will, they're just not space filling, right? Yeah. They're only filling a couple % of the volume.
Yeah. If you have too much water, it does mean the colloid particles will come together, phase separate from the rest of the water. Does that mean that?
They will want to phase separate. So you can think of this as the colloids undergoing a spinodal decomposition, and it's arrested in the middle. So they don't have time to completely phase separate. Locally, in this case, the attraction is so large that they never have time to really fully phase separate, because if attraction is really large, the way to think about this, Zhigong, is you have to understand a bit about the kinetics. If I have two particles, they diffuse around, eventually they hit. They stick to one another. Then I have like two chains, and they start diffusing and they start hitting. Because they diffuse, they can't really diffuse in, because as soon as they hit, they stick. And that's what gives them this tenuous structure. The fact that they're diffusing actually prevents them from diffusing in, because think of it this way: if I do this and I want to have them go like this, they diffuse, they go like this. But as soon as they diffuse, as soon as they hit, they touch, they stop. And so they can never diffuse in. And so that's why the motion of the particles is intrinsically related to the structure of the gel. And so it's always a very open structure.
Yeah, I want to just see whether fracture of this colloidal gel, because a colloidal gel is different from another colloidal gel. You have several types, right? I don't know how much people actually study them just itself, not in just a colloidal gel fracture. It might be interesting. Yeah, if you're interested, you can ask Shijie, this student you have, talk to me. Because we work with fracture everything, but I cannot quite picture or this yet, because I don't know enough your material. Yeah.
I will ask CJ to talk to you because he's at his heart, he's also a theorist. So he's an amazing guy. He's just an amazing guy.
Yeah, he is a mechanician. He was my teaching fellow once, but then he never took serious fracture mechanics course.
He's become a really remarkably good student. I really like him.
Yeah, all right, okay.
He can do anything now.
Excuse me. So may I follow up Professor's question here? Just the last comments about the question just the Professor proposed. So here, when you talk about the material using in your experiment, is different from the material Professor used in his experiments. So I'm just wondering, how can you make sure the material you are using is kind of comparable to the crystal material? Thank you.
I would say it's not comparable. In fact, it's very different. They're both colloids, but they undergo very different interactions. And so the stuff that we do with Franz is really quite different. It is crystal. And the person who, Franz, of course, knows infinitely more than I do about the material side of how it behaves. I know a lot about the colloid side, but he really understands the crystal side. So he'll know the right terminology to use. But I think that there is no real cohesion there because the particles remain crystal purely from entropic reasons. Just if they didn't diffuse, they wouldn't be crystalline.
I see. Because at the beginning you mentioned the fracking, is the real thing, the fracking in the crust. So yeah, I suppose your experiment should be comparable to the fracking in nature.
Well, I think the second part, I hope, is somewhat comparable. The gel is a little bit more tenuous as to whether there's a comparison because there's so many different, so much different physics going on.
Yeah, can I jump in just a little bit? Since I've actually worked with Ludax a lot, so we also took the scanning electron microscopy with the pack. So depends on maybe the surface chemistry and also how slow you dry. Those particles can sometimes packed into really close packing structure. Even if you have monodispersed particles, you can even got the colloidal crystal. We actually see that. And if you have a biodispersed or polydispersed, you can get a colloidal glass. And also, I think if you have really good cohesive between particles, you can get this more porous structure. This all depends on the cohesion between particles. But yeah, this can be a very rich material of all this colloidal gel under the drying. And there maybe one of the very familiar and practical example is the paint. I think paint industry really cares a similar problem like the first part of what Dave talks about. Yeah, that's just my comments. Thanks.
Yeah, so yeah, thanks a lot. And I would say that I agree with you completely. I think we can make some estimates as to the forces that drive it, because it's surface tension that must be driving it. And so it's it's the surface tension divided by some fraction of the radius of the particles will tell me the stresses that I can get. And that will be the stresses that drive the particles together. And those can be huge, right? Because if they're,
exactly.
let's say 10 nanometer
Especially
particle, then I would say that it's maybe 1 nanometer, radius of curvature of a nanometer, which is, surface tension over a nanometer is probably, what, megapascals at least? All right. A micron, surface tension for a micron is a tenth of an atmosphere. So a nanometer is 100 atmospheres.
Yeah,
so that,
exactly.
Megapascal. 100 atmospheres? No. 100 is 10 megapascals.
Yeah.
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 So that's the kind of
there's
that you get. That's what's going to drive things together. And then once you do that with Ludox, you start pushing the surface together. It actually starts to coarsen. The silica itself will start to flow, and then you get even stronger bonds. At least I'm pretty sure that that's the case.
Yeah, and also there are actually different kinds of Ludox to actually check. There's from the different models, like they have different surface chemistry, particle property. Yeah,
yeah,
that's a good model system.
Yeah, it's a great model system.
Yeah, no, Dave, so the other thing, just a comment, maybe a suggestion. So you have developed these tools measuring, map out the deformation field at high temperature, time and spatial resolution. That's what you do. Yeah. But in fracture, of course, there is some unsolved problem. Many problems are kind of solved. Because if you want to know elastic field, I don't know what a deeper question you can ask anymore. But there is one problem called ductile to brittle transition. I don't know if you heard this phrase. Essentially, it's something like simple. So some material at a low temperature, just when you do applied deformation, it just fracture brittle. But when you just go to a little higher temperature, then the material just flow like metal. So steel actually does that. Go to low temperature, it's a fracture like a glass. At a high temperature, it flows like a metal. There's a ductile to brittle transition. Temperature happens at a very narrow range, 10 degrees or something. People have worked on this, Jim Rice, people work on this, speculations, but never people can see things clearly, what's going on, because these are atomic things. So this transition is essentially a mystery. But maybe you can crack this, just because you can see many things simultaneously. Individual particles, what's going on? Ductile to brittle transition. It's essentially an unsolved problem.
You're making me intrigued. I'll have to come and talk to you to learn more about it.
Yeah, be delighted to talk to you. You have so many experimental techniques, but I hope some of the techniques will be used to answer deeper questions in fracture.
Well, it's a matter of my ignorance, as always. Know what the questions are.
So one thing,
well,
probably
send CG to talk to you, and you inspire him to think about that.
Yeah. Please do. Yeah, he and I talked before. He was my teaching fellow.
Yeah. No, he would. If you can get him curious, he'll do it.
Yeah.
So Jiga, when Dave's student talk to you, and I'm actually very curious about, for example, if you can really see all this displacement field and the strength field. So for example, what is the singularity at the crack tip of this material? This is something you can really see and measure, right? So this is something really hard to see in other materials so far. That'll be very interesting.
I think Ye have done this before, right? Using traction force microscopy. A long time ago.
Yeah, but back then we're not at the single particle level, but with a slightly larger particle, maybe we can do that.
Yeah, but I think the point is that you want to, if you want to see small motions, you want to do an interference measurement. I think that's the advantage, and so we do traction force as well, and that's great. That's a good measurement, but it might be that there might be other ways of making the measurement that take advantage of the particles in a different way.
Yeah, we're working on that. Stay tuned.
I'm sure you are. I'm sure. I'll definitely stay tuned because I'm sure it's interesting.
I'll talk to you soon.
Great.
Sorry, Professor Weitz. I have one question. Sorry, I apologize for interrupting. Actually, it's rather related with the Professor Sua's question about maybe it is related with the ductile to brittle transition. So you measured the flow field and velocity field ahead of the crack tip. Did you measure or did you calculate the Pecklet number just ahead of the crack tip?
No, but I'm pretty sure there's no diffusion. So the Pecklet number is either large or small, whichever the one. I forget whether it's high or low when there's no diffusion.
Can you give an order of magnitude about the Pecklet number?
No, I can't. I've never calculated it, but I just don't think there's any diffusive motion. But I don't know for sure.
Yeah. One additional question then. Now, normally we use Stokes flow in order to model such kind of a problem because of the low Reynolds number. And Stokes flow is valid when the rate of deformation is low. So can we still use Stokes flow because the rate of deformation ahead of the crack tip is, I assume that at the, just ahead, at the instant that the bonds are broken, the rate of deformation shall be very high. So can we still use it, or what is your opinion about it? What type of
in the case of the colloid system, it's all slow enough that you can. In the case of the PMMA, the hard system, I'm not sure you can use Stokes flow. I don't know. There you be. It may not be.
Okay, thank you.
All right. Hey, John, you're our leader.
Yeah.
Are we wrapping up?
Yes. I think it's like a great talk. Thanks very much for Dave again. And thank everyone for joining the discussion today. I also learned a lot. Not very familiar with this colloidal gel before, but it's very interesting. And thank you everyone for joining. And
thank you everybody. It's been a lot of fun.
Yeah, thank you.
Thank you.
Bye. Thank you.
Bye-bye.